and other advanced analysis. So let's get started. But first, let's review our work from last week. So we've built from week 1, where we talked about interpretation of descriptive analysis, and then last week we talked about we talked about the idea of statistical testing. Now, that's something most people get very confused. So we want to really make sure that we all leave perfectly understanding the concept of hypothesis testing. Obviously, that underpins everything we're saying from week 1 to week 3. So if we don't leave home with that concept really clear in our minds, that means we've not achieved the purpose for this 3-week seminar. All right, so we have a quiz here. So here are the rules of a quiz. I'm going to look into a mirror. If what I see in the mirror, if the guy outside the mirror is the same guy in the mirror, then that means, well, it's true, right? So the null says that the man outside the mirror is equal to the man inside the mirror. Are we all fine with those rules of engagement? It's a very simple rule. The guy outside must be the same as the guy inside. If it's true, then, well, the null is true. All right. So if we're all fine with that, what do you see on this page? This is the guy looking outside the mirror. Inside the mirror, you see his image. So the question is simple. Is the guy outside the mirror the same as the guy inside the mirror? What do we say? And I promise it's not a trick question. All right, so how come look, this is just the first slide. How are we getting off on such a rough terrain? On the very first question. I did not expect this would be any controversial issue. Oh, please, don't. You guys are reading too deep into it. Forget about the color hues and all, right? Does it look the same? It's not a deep question. It's not a deep philosophical question. But by and large, do they look the same? Yes, they look the same. All right, so the guy outside the mirror is the same as the guy inside the mirror, so we say that the null is true. Remember, we said null says there's nothing extraordinary happening here. Obviously, when you look into the mirror, you don't expect to see something different. You expect to see your reflection, right? And last week, we established that everything in life takes place under the null. So if I look into the mirror, I expect to see myself. I don't expect any surprises. So if the guy looking into the mirror is the same guy as the one outside the mirror, then we say, well, the null is true. So this is the first scenario. Now let's go to another scenario and let's see what happens next. So here, scenario number 2. The same guy looks into the mirror. Now, what do you say? The guy outside the mirror, the guy inside the mirror, are they one and the same? We would like somebody to raise their hand and tell us if they're the same, and if they're not the same, what has changed and what has not changed, and what conclusion they might draw from this. Who wants to take a stab at that? So it's not a trick question at all. I promise you. It's just the guy outside the mirror, the guy inside the mirror are the same. What has changed from the previous slide? What has not changed? And what conclusion will you draw?
Jennifer, you can unmute. Okay, Jennifer, Jesse.
Thank you very much. Prof, they are two different.
Okay.
The one inside the mirror look like an animal.
Okay.
And the one outside the mirror is a human being.
All right, thank you. So what has not changed when we compare with the previous screen? What has not changed and what has changed? Okay, maybe somebody else. If we've lost that person.
Okay. Emmanuel? Emmanuel, can you unmute?
Okay, yeah, Prof. What has not changed is the guy outside the mirror.
Excellent. And what has changed?
The image in the mirror has changed.
Okay. Now, while we're still here, the guy outside the mirror, what does that represent? So we have a mirror and we have what is outside the mirror. What does outside the mirror represent?
Human being.
Human
Okay.
being.
Or if you want to generalize, the mirror is what and the outside the mirror is what?
Inside the mirror is ostrich.
Okay. All right. If we're to generalize, right, which is reality, which is not reality?
So the one outside the mirror is the reality.
Exactly. So in the two instances, reality has not changed. We also call reality the true state of nature, right? That has not changed. The same, what we had in slide 1 is exactly the same guy, slide 1 and slide 2. The state of nature has not changed. Now, what has changed? What the mirror, what exactly is it? If the state of nature is what is outside the mirror, what do we call what is inside the mirror? In the context of research, what is that? The mirror represents what?
Influence.
Okay. What else do you think?
It could also be factors. Which
The mirror is your study. Let's put it that way.
Okay.
Okay. The mirror is your study. So we have the true state of nature and what you're trying to capture in the mirror, which is what you're trying to capture in your study. If this is the true state of nature and you capture exactly that, well, that's the truth, right? You know. Now, if here in this case, the true state of nature is this, and this guy looks into the mirror and he sees something else. Now, what he's seeing is this something flattering or is it not flattering? What do you think? What kind of animal? What does he see in the mirror exactly?
Ostrich.
Okay, I don't know if that's an ostrich per se. And who wants to give another try?
It's a
I don't think
bird.
ostrich is that colorful.
It's
It looks like peacock.
Yeah, it's
Peacock.
a peacock, right? So the guy looks into the mirror and he sees a peacock and he's saying, oh, I am so significant. I am so elegant. I'm so powerful. So clearly, do we all agree that there's an error going on here?
Yes.
What
And
kind
it's
of error?
flattering.
What kind of error will that be?
Type 1 error.
Why do you say it's type 1 error?
Because he's supposed to see his own reflection, but he's seen another thing.
Okay. He's not seeing not just another thing. He's seen another thing that is what in relative to himself.
No, that thing is not relative to himself. That one is an animal, a bird.
True. But what he's seeing in the mirror, right? Is it more flattering or less flattering? That's the point we're trying to drive at.
Okay. You
Prof,
can say is
I think it's more flattering.
Exactly.
Yeah.
He's seeing something in the mirror, right? Now, it's not just enough for us to say he's seeing something different in the mirror. The question is, what different thing is it in the mirror? Is it more flattering or less flattering? So, because there are three kinds of things you can see in the mirror, right? You can see yourself, sure. You can see something different, which is more flattering. And you can see what he's saying here. He said, I'm so significant, right? I am so powerful. I'm so elegant. It's like, dude, that is not you, right? That is not you at all. What you're seeing is a peacock, and you're so full of errors now because you imagine that that's you. But that's not you, right? So, they, as the guys on social media would say, this is Delulu, right? the Lulu on this one is quite strong. The Lulu index on this is pretty high, right? So this is type 1 error. Type 1 error is exactly when you look into the mirror, instead of seeing yourself, you're seeing something else that is way more flamboyant, way more appealing. So in the context of a study, you come up with a study and say, oh, my study found these significant things. That is not true. You do not find, there's nothing like that in the state of nature. You're just finding things that don't exist, right? You've looked into the mirror, and instead of you finding nothing or just finding nothing out of the ordinary, you have found all of these things that are out of the ordinary, and you're declaring that, oh, my study is so significant and I'm so elegant. That is not true. You're just making up stuff because the law in your study is quite strong, right? Now let's go on to the next one. So same guy here looks into the mirror, and now what he see in the mirror, is it the same as what is outside, or what do you conclude here?
Kenneth, can you unmute? Janet? Not speaking.
Prof, can I try?
All right, please go ahead.
Okay, I think he sees something less of himself.
Okay. And so what kind of error will you declare that to be?
I would say type 2 error.
And why will you say that?
Because, outside the mirror, he looks more brilliant and elegant. Then in the mirror, he looks less of himself.
Exactly. So if we apply this to a study, what will that describe?
So in a real world study, we will say that perhaps the sample size is less to be able to, generate a result that could actually represent a change.
Okay.
Or that would detect a change as minimum as
All
you
right,
could
thank
do.
you. Thank you. Does somebody else want to, you're correct. Does somebody else want to represent that in another way in how they understand it?
Yeah, Doc,
Can I
Prof,
try?
Prof, can I try?
Okay, let's Kenneth. Kenneth, go ahead, please.
Was that not Kenneth?
Oh, sorry. Lungile, please don't
It's
choose.
David.
I choose the wrong person.
David?
Hello, good evening.
Hi.
Yes.
Good evening.
Yeah, we can hear
Can
you
you hear
clearly, David. Yeah, please go ahead.
Yes, I think what he's seeing is different, is not the real state of things, but he is underestimating what is.
Okay.
Hello?
Yeah, we can hear you clearly. We
Yes.
heard you clearly. Thank you.
Yes.
All right. We would like one more person to give it, and you're all correct. Just one different perspective. So we'll have one more person to give us their own interpretation of the picture.
Let's try Regina or Regina.
Hi, thank you. I think basically we're saying that the sample actually has significance to what the actual picture has, but the researcher concludes that the results from the sample are not as good or as significant or as representative as what they would have assumed it to be in the first place.
Exactly. So again, remember, in all states, we're comparing your study, which is the mirror, with a true state of nature. True state of nature says, well, it's significant. Your study says, oh, I'm shy. I'm very timid and shy. It's like, dude, you're significant. Like, no, I'm not. I'm shy. That's type 2 error. And from what we discussed, what is the most common reason for a type 2 error? We should be very familiar with that by now. You'll see answers in the chat. Yeah, small sample size. You're all correct. Yes. So small sample sizes are what will give rise to a type 2 error. Now, is it possible that you would have both a type 1 error and type 2 error coexisting in the same study? What do you think? We want somebody who to pick up that and answer. So if you can volunteer and raise up your hand and answer the question. Can you have a type 1 and type 2 error in the same study? And if you're answering, you must give us a scenario where that will exist. And if you're saying no, then you have to defend why that would not make sense to you. Because this is the foundation of research. We really need to understand this very clearly. Yeah, I can see your charts, but I need somebody who is confident enough to raise up their hand and let's have a healthy debate about that answer. Who wants to try? Abubakar Abdul Karim.
Yes, sir. We can have type 1 and type 2 error in the same study.
How would that happen?
For example, mixed methods.
Okay. All right. Let's stick with quantitative studies, right? In the context of a quantitative study, how would you have both type 1 and type 2 error? In what scenario? Can you paint a scenario where you would have type 1 and type 2 errors coexisting together?
In quantitative study.
Yeah, that's correct, yes.
Yeah, I don't think we can have it in quantitative study, but we can have it in qualitative and quantitative study. That's from the philosophical point of view.
Okay. But just to be clear, type 1 and type 2 errors, the full names are type 1 statistical error and type 2 statistical error. Both of those errors have to do with quantitative studies, so that we're very, very clear about what we're talking about and we're all on the same page. So they're all statistical issues that have to do with quantitative studies.
Okay, right. It is all statistical error. Yeah, if it is in that case, we can have it in quantitative study.
Okay.
If it's statistical error.
Okay, so I want a scenario. I want somebody to paint a vivid scenario where we can have both type 1 and type 2 error coexisting together. Because you need to have this shouldn't be just theoretical, right? You really we're taking a lot of time with this because it's a foundational research. You need to know when you're going into the bush in your own research and when you have to come back and say, oh, no, this is not going the right direction. So for that to happen, you need to be able to provide a clear, picture of when things could go wrong. Charles, Chibisi, do you want to take a stab at that?
Yes, Prof. Yes, Prof. So it's possible. It's possible to have a type 1 and type 2 in the same study, because like I can, for example, let me use myself now in this scenario. I've conducted a study, on a particular issue, and I decide to report, interpret the data, to reject the hypothesis, so the norm, which is supposed to be that nothing extraordinary, should happen. So I'm rejecting that because of already the biases I already have, or I had before the interpretation.
Thank you.
So yeah. So the type 2 now could be that, I'm now failing to also reject the false norm of the other way around in the same study as I'm trying to interpret. So that's my own. Yeah.
All right, thanks. Pastor George, you have a very insightful answer, which we really have to explore further. Do you want to explain expand on your answer? I don't know if George is still here. If you're not here, I can just read out your answer.
George, you can put up your hand. Let me unmute you.
I'm not sure if it's Pastor George or how you pronounce the name, but your answer is exactly what I was looking to hear. Okay, I'm just going to read out his answer here. George says, a very small sample size where the researcher does multiple comparisons. That is exactly, put in the most simple way, that is exactly what we're trying to get at. You have a very small sample size and you are doing a lot of comparisons. So the small sample size already sets you up for type 2 error. And then within that small sample size, you are doing so many comparisons, comparing A versus B and A versus C and D versus E and all manner of comparisons. So yes, it's possible for you to do p-hacking in the context of a small sample size, which sets the perfect storm for the coexistence of both type 1 error and type 2 error. So you are doing a fishing expedition in a small pond, right? So clearly you're setting yourself up for both type 1 and type 2 error. Again, we've taken quite a lot of time with this concept because it's foundational to research. There's no point in research if we don't even understand this concept, because these are the foundations of research. All right. So now another pop quiz for you. Why do we say that we fail to reject the null instead of accepting the null? Have you ever wondered why we use that language? We always say, oh, we reject the null or we fail to reject the null. Why don't we ever say we accept the null? Who wants to answer that for us?
Charles, is that a good hand or you want to answer? Okay, Kenneth, you can unmute.
Okay, yeah. So, Prof, I think that because the now is what we already have in the system, what it's already existing, what is already accepted, and so we kind of cannot accept it again. That is what I think.
Okay, thank you. Who else wants to give us a different perspective? Again, this is just to make sure we're all speaking on the same, we understand why we say what we say.
Yeah, thank you. I think null is, it seems like a normal condition. Everything is occurred in a normal condition. Normal. That's why we will compare it with quite different.
Okay. All right. So let me just explain it so that we can get in our way. The null hypothesis, think of it as in a very simple way, think of the null as the enemy, right? The alternative hypothesis is what we really, really want to prove. That's where we really want to get to. The only thing standing in our way is the null, right? So I put up this image of the Geneva Convention for treatment of prisoners of war, just to make a point. So the handbook on prisoners, the rules of war requires that you respect the prisoners of war and you treat them well. Well, what the Geneva handbook does not require you to do is to love them. Well, you don't have to love them, but you must treat them well, right? The same thing with the null. Think of them as the enemy. We don't have to love them and accept them, but we can only fail to reject them because they are what stands in our way to getting to the alternative we seek. That's just a very simplistic explanation, but I hope you get the picture. Well, all of that is just a review of last week, which was about bivariate tests and the foundations of hypothesis testing. Today, we're going to go ahead to talk about the interpretation of odds ratios and multivariable analysis and all of that. So again, first things first, we want to make sure we get our terminology right. And so first order of business is to understand the concept of odds versus likelihood. So odds represents the ratio of the probability of an event occurring relative to the probability of that event not occurring, right? And we have a formula for it here. So odds is equal to prevalence all over 1 minus prevalence, or odds is equal to the probability all over 1 minus probability. So it's the probability that the event occurs divided by the probability that the event does not occur. You can also say it is the likelihood that the event occurs divided by the likelihood that the event does not occur. So when you have likelihood at the top and likelihood at the bottom, what happens to the likelihood? Who wants to answer that question? It's a simple question. It's not a trick question. Likely over at the top and likely at the bottom, what will they do to each other?
Okay. So them you can mute. Okay. Something.
They cancel out.
Exactly. They cancel out. This is why, again, remember what I'll focusing today on interpretation of results from multivariable analysis, starting from logistic regression. This is the basis upon which we don't want to hear certain words from you when you're interpreting results from, let's say, odds ratios. Like some words that we don't want to hear from you are words like likelihood, right? Why? Because we just explained why we should never hear that. Odds means likelihood over likelihood. The likelihoods cancel out each other. So you cannot use the word likelihood when you're describing results from odds ratios because it's not likelihoods. I hope that makes sense to us, right? You also cannot use the word probability because it's probability at the top divided by probability at the bottom, which means they cancel out each other. So we're going to go over now and look at some worked examples of how to interpret the results from, odds ratios. And again, the taboo words we absolutely do not want to hear are the words likelihood. So I'm going to call on you, and anybody who says that uses the word likelihood, we're going to have to kick them out because they seem not to understand this equation or this formula. All right. Let us look at some of the words, but before we go on to some worked examples, let's explain some terms that we need to understand first before we get there. We need to understand the concept of binary outcomes. Binary outcomes are outcomes that you have 0 and 1. So for example, dead or alive, smoker or non-smoker. And this is important for many kinds of regressions that are binary, that require a binary outcome. So for example, if you're using probit regression, if you're using binary logistic. As a matter of clarity, please avoid just saying logistic regression when you're using that in your analysis, because there are so many types of logistic regression. So please try to be very, very specific in your language. If your results are from a binary logistic regression, please articulate it very clearly, because that is not the only kind of logistic regression that exists. You also have multinomial logistic regression, you have ordinal logistic regression, and many, many other types. So for clarity of language, if your results are, and most results that when people describe logistic regression, what they're actually talking about is binary logistic regression. So please, it's just one extra word, but it makes a whole lot of difference. So please just don't just swallow that word, okay? Please just put it there for us so that we can understand clearly what you're doing and how to interpret it correctly. So that's the first thing we want to make sure we clarify so that we're all on the same page in terms of interpretations. We also want to make sure that we don't endow our interpretations with causal might or causal ability. When we use observational data should be interpreted in the context of associations, not in the context of causality, right? And those are very different in how we interpret them. They're also very different ideologically or philosophically, right? It's not just practically. And this is a very nice distinction of the difference between what happens when we interpret them as causal relationships versus as associations. So here you have the population of interest, and you have those who are exposed or non-exposed, right? Or treated or non-treated. When we look at associations, what we are saying is that the odds of the outcome among those who were exposed, right? This is the white, compared to those who were non-exposed. So we're actually taking the original individuals who were exposed and comparing them to those who are non-exposed. This is what happens in the real world. So this is what, on the right-hand side, is what happens in the the real world in the context of observational studies. So we're looking at the expected outcome conditional on A equals to 1, which is the expected outcome when A equals 1 or when you're exposed, compared to the expected outcome when exposure is 0. This is what's happening. In causal models, it is a completely different thing we're doing. What we're doing is on this left-hand side. We are creating counterfactual scenarios. Counterfactual simply means it does not exist. It exists only in our imagination, right? It's a hypothetical scenario. So we're creating a scenario where everybody was exposed compared to a counterfactual scenario where nobody was exposed. This is what causal models, this is what they do. This is what we do when we fit causal models. We take that original society or population, and we fit a mathematical model in which everybody is exposed, and then we'll fit another model where we assume nobody was exposed, and we'll look at the differences in the outcome between those two. So the way we interpret causal models is very, very different relative to how we interpret associational models. Even the way we depict them mathematically is different. So you can see here, we're using superscript, right? Expected outcome in a counterfactual scenario where everybody's exposed versus the expected outcome in a counterfactual scenario where nobody's exposed. We use superscripts when we're talking about, causal models versus in this case where everything is just regular text. So this is the moral of the story here, is that those two things are not the same. And when you're interpreting your results, you want to be very careful with the kind of terminology you use, because some terminology might suggest that you're referring to this when in actuality you are referring to this, right? So words like cause, the effect of so and so, the impact of so on so, right? The attributable, all of those words belong to the left-hand side. Well, again, impact, effect, cause, or attributable, all of those things are words that indicate causality, and you should try to avoid using them when you're referring to associational models, because those words suggest causality, right? Again, we're just trying to set the rules of engagement so that when we start interpreting results, I don't want to be hearing some words that we have already said are an absolute no-no. So that is something we also want to understand very clearly before we go into the interpretations. All right. And then the third thing we need to understand is also the terminology. There's a lot of terminology which, we tend to misuse or abuse. So we want to get it right. Univariate and bivariate are not the same thing. Uni, from just the etymology, means one. Unit, right? We say uni means one. Bi means two. So bivariate or binary, right? They all mean two. So univariate, this is an absolute no. In univariate analysis, mean age do not differ by race. This is wrong language because you are looking at two variables, age and race. Once you have two variables, that is no longer univariate. That is bivariate. A univariate analysis will be saying, oh, the mean age was so. But once you now start comparing the mean age by other things, that's no longer univariate, it's bi. Bi 2, uni 1. So the correct language would be in bivariate analysis, mean age did not differ by race. So that's correct. There's also a distinction between multivariable and multivariate. Now that's kind of confusing because they both start with the word multi, but they mean very different things. Multivariable means 3 or more variables with only one outcome. Multivariate means 3 or more variables that are all on the same footing. That is, there's no one specific outcome. Now, 99% of the time, when people refer to multivariate, they actually mean multivariable, right? So we want to make sure that we all are familiar with the same terminology and that we're all singing from the same hymn book, so that we're not saying potato when we mean potato. So here, for example, this is wrong. They say multivariate logistic regression with queries as the outcome. Okay, so clearly you have only one outcome. and you're looking at a bunch of predictors, that's not multivariate, that is multivariable, which is what we have in the second option here. So let's put it in the picture, because we all love pictures. The picture is worth 1,000 words. All right. So let's see if you can guess. I need somebody who would guess. I'm not sure why I showed you that earlier, but anyway, you have one outcome, one dependent outcome, and 0 independent outcomes. So one outcome, no predictor. What do you call that kind of analysis?
Univariate.
Okay. Excellent.
It is
So
called univariate.
all right, so for example, overall means, overall medians, overall descriptive analysis that are just at the overall level. We're not looking among that variable stratified by other variables. It's just that variable, overall mean, overall median, or things of that nature. Those are all univariate analysis. Now you have one outcome, one predictor. What kind of analysis is that?
Joseph,
Bivariate. I think it is bivariate.
Okay. So we have bivariate, that is one variable, one predictor variable, and one outcome variable. So for example, now we're no longer just looking at overall mean, but we're looking at the mean of, let's say, the mean height among males versus females. The first scenario was just, what is the overall mean height in the overall population? So we're just looking at one variable, the mean or the average of the height in the whole population. But now we're not looking at the whole population anymore. We're saying, what is the height among males and females? So now it is height and gender. So that's two variables. We're looking at height across levels of gender. So that's bivariate. All right, we have one outcome and two or more predictors. What kind of analysis is that?
Amina Suleiman.
That's multivariable.
Excellent. So that's multivariable. Because we have one outcome and we have two or more predictors. So when you say, logistic regression or adjusted logistic regression, you're referring to multivariable analysis. And then you have two or more outcomes, and you have, one or more predictor. What would that be?
Joshua Oji. Joshua, you can unmute. Okay. Desalegn.
Yeah. Multinomial.
Okay, another try.
George.
Yeah,
George, you
that's
can
multivariate.
That's multivariate, that's correct. So this will actually be 0 plus, not 1 plus. Because it's possible that we can have 2 plus and no predictor, in which case all the outcomes are on the same footing. So for example, when we do factor analysis, or we do principal component analysis, all the variables in the analysis are outcomes. There's no predictor per se. So let's change this to 0 plus as opposed to 1 plus. Okay, there was another one at the bottom. Okay, already. So that's fine then. All right, so let's make sure we use the right terminology, because that's very important. People use this as interchangeable. There are huge differences amongst them, factor analysis and principal component analysis, but that's beyond the scope of this class. Maybe we'll have another session where we'll just focus on that. But for now, we just want to focus on terminology, using the right language, and interpreting the results the right way. All right, here is the pop quiz. This paper is looking at the cigarette prices among different products. What kind of analysis is this? Oh, dang it, I've already shown you the answer. But Who wants to explain why this is univariate? Like, why is that the answer? Who wants to explain to us? Why is this not bivariate?
You can put up your hand. Okay. Jeremiah.
Yeah, it's univariate because it's all focusing on prices.
Okay. All right. So it's just focusing on prices. Our analysis is not stratifying prices by tobacco products. That's just this is just how the data were captured, and we're just presenting the data that way, right? So that's what makes it univariate. The same thing here. This is just looking at number of hookah bars by city, in the 100 US largest cities. That is still univariate. Now, this is bivariate because this is looking at the prevalence of menthol cigarette among current smokers over time. So here we're looking at the percentage who reported menthol cigarettes, and we're looking at time. Time is a variable here that makes it bivariate. So you can ask the question, did the prevalence of menthol cigarette change significantly over time? The answer could be yes or no, right? And so look at there's a mathematical basis for generating a p-value here because we're looking at two variables, the prevalence of menthol cigarette and time. This is also bivariate because we're looking at e-cigarette use on one hand and the type of cigarettes that smokers use on the other hand. So we're saying smokers who use menthol and those who use non-menthol, is there a difference in their use of e-cigarettes, right? So there are two variables involved here. The type of cigarette smoked and whether or not they use e-cigarettes. So we're now looking at whether there are differences in that distribution. So this makes it bivariate. Now, this is meant to clarify any confusion you might have that we don't say something is bivariate or multivariable just because of the number of variables you are seeing on the screen. You can see a lot of variables on the screen. That does not necessarily make it multivariable, right? What makes it multivariable is really what is being tested. So here we're simply looking at the percentage of individuals who support bans on characterizing flavors by these different characteristics. So this is the overall percentage who support bans on characterizing flavors in the overall population. And then this is the percentages by gender, by age, income, and so many other variables. So in each case, we're looking at that percentage in that group alone. Here, we're looking at the percentage for support only by age, only by income, and so on and so forth. So let's not get confused and start thinking that if you see a lot of variables on the screen, then it's multivariable. That is not the case. The multivariableness has to do with whether or not we have multiple variables in the same analysis at the same time, not that we have two variables being assessed separately within different analyses. Now, this is multivariable. Why? Because we have several variables being included in the same analysis at the same time, right? So we're going to focus on interpretation in a minute, but this is just to show you how it might look like. This is also to show you how you are expected to present your results from regression multivariable analysis. So according to Strobe, Strobe is an acronym. It stands for strengthening the reporting of epidemiology in observational studies. It is a checklist that tells you or tells researchers who are using observational data the do's and the don'ts of how to report data. So I'm going to just summarize the key elements of the Strobe criteria using this picture. Now, Strobe requires that when you're presenting results from your analysis, number one, as you can see, your crude results and your adjusted results should be shown together, right? So now, this is obviously the gold standard way according to Strobe. Now, in practice, people may do it a bit differently, but we all, of course, in a class like this, we should focus on what is the gold standard approach that is recommended. So And especially if you are writing a thesis or a dissertation, of course, you should do things by the book. So when you're reporting the results from your analysis, present your crude odds ratios and your adjusted odds ratios. Clearly label the 95% confidence intervals very clearly so we know what we're talking about. Write things in full. Don't just say AOR and expect your reader to guess what AOR means. AOR could mean anything under the sun. So put adjusted odds ratios and crude odds ratios. The crude odds ratios should come first. Well, because that is how we analyze. We do crude results first, and then we do adjusted results. So present your crude results first before you present adjusted odds ratios. Note that there are no p-values present in this table. If you have presented your results with confidence intervals, you don't necessarily need to show us the p-value again. We can read. we can read and know that these are significant and these are not significant. Now, if you really want to go the extra mile, see how the author has boldened the ones that are significant. Yeah, you can bolden them and say so that it's just easier for us to detect them at first glance. But there's absolutely no need for you to display confidence intervals and then now put p-values. You know, it's always a good thing to have white space in your tables. There's absolutely no need for you to now cram every single inch of your table with a statistic or a number. Just have pity and have mercy for the people who are going to read your paper. Like, you know, so less is more. That's the point we're trying to make here. Less is more. So leave a lot of white space so it's easy to read. Use a font that is large enough. I would recommend using 0.10 or 0.11, or even 12 if possible for your tables, so they're legible. Don't squeeze everything into a font size 6 or 7. That it makes it very hard to read. Use fonts that are very legible. This is, I believe this is Times New Roman or Arial. Those make it easier for you to read your tables. So crude odds ratios with 95% intervals in the first column, and adjusted odds ratios in the second column. Now, if you are dealing with a number that has the potential for negative values, please do not use dash. So here, odds ratios cannot be negative. That's why we're using 0.90 dash 1.49. But sometimes you could be dealing with a quantity that has negative values. Like if you're dealing with means, if I'm trying to look at, let's say an outcome is your account balance. Well, account balances can run from negative to positive. If you're super broke, obviously your account negative is going to be negative. So in that case, the negative, the point estimates or even the confidence intervals might have valid negative values. When you're dealing with such a scenario, please do not use dash to indicate the range of the confidence intervals. You can just say, you can use comma instead, or you can just use the word to, T-O. So in that case, it will be 0.90 to 1.49, such that if you have negative values, it's not confusing. The user will not confuse the dash indicating range with negative values. All right. When you are displaying the first column here, you should make it very clear what the reference category is. The reference category is what we are comparing the results to. So the reference category should be very clearly indicated in the output. So here you have sex, the reference is male, and then we have the other categories. There's no hard and fast rule how you want to display the reference group. You can indicate with an asterisk or whatever, but it should be clear to the reader what the reference group is for that indicator, right? So that is very, very important. So it's clear so that the results can be interpreted easily. So that is, in a nutshell, that is what you are expected to do when you're presenting results for regression analysis according to Strobe guidelines. We're going to drop the link to Strobe guidelines so you can spend your time to, and I'll encourage you to read it so that you're familiar with what the gold standards are. Now, let's look at some of the other rules as far as just presentation. Make sure that there is consistency in the number of decimal places you report. So here, in general, we follow the 1, 2, 3 framework for reporting of results. In other words, percentages are reported to 1 decimal place, odds ratios are reported to 2 decimal places, and p-values are reported to 3 decimal places. So that's what we mean by the 1, 2, 3 framework in terms of number of decimal places. So odds ratios always report them to 2 decimal places, and they should all be in 2 decimal places. So in other words, if you have 1.6, it is not enough to just say 1.6. You should write it as 1.60 so that it is full 2 decimal places, right? If it were just, let's say, 1, if it were just, let's say 1, it will not just write it as 1, we'll write it as 1.00 so that it is consistent. We have consistent rendering of the number of decimal places. So that is that for consistency, so that it's very clear to read your work and to interpret it. So those are just some few guidelines that we would just like to emphasize when you are presenting your results in terms of odds ratios. Now, in terms of while this lecture is more about interpretation, you know what, I want to talk about, rules for selection of variables, but let's just stick with the agenda. We can have that as the next session, like how do you choose the variables that go into the regression model. So we just focus on the agenda, which is just the interpretation and the presentation, and maybe next time we can focus on the actual mechanics of selection of variables into your regression. All right, let's move ahead. So structuring of analysis, univariate, bivariate, multivariable. This is the order in which you should perform the analysis. This is also the order in which you should report the analysis. So like we said, one variable analysis or univariate analysis have to do with how a variable is summarized, percentages, means, medians, whether weighted. Bivariate analysis, you have to report on the kind of statistical test you use. Were they parametric tests or non-parametric tests? Were they two-tailed or one-tailed? What was the p-value threshold? And then multivariable analysis, what kind of regression model did you use and why? And you have to list all the variables in the final model and the software you use to analyze it. So these are the kinds of analysis we are focused with when we describe univariate analysis. There are questions like, what is the mean value of X? Or what is the median of X? Or what is the count of X? Or what percentage of people reported X? Those are all questions that have to do with univariate. As you can see, the only variable involved here every single time is X. We're not saying X versus Y. Once we now introduce Y, that's no longer univariate. That is now bivariate. So in each of these questions, we're focusing on just X, nothing more, nothing less. So this is univariate. In bivariate, it's not just X. It's X and something else. So, but it is only X and something else. If it's X, Y, and Z, that is no longer bivariate. It is X and another variable. So in this case, what is the difference in the mean value of X between the groups of, of the second variable? Let's say the second variable is gender. So the levels of gender are Y and Z. So we're saying, how does the mean height differ between males and females? Of course, males and females are both categories of the second variable, which is gender. So those are the kind of questions we explore within bivariate analysis. In the same way, how does the median height compare between males and females? Again, males and females are not two different variables. They are just different categories or different groups of a second variable. So bivariate analysis always involves only 2 variables. If it involves more than 2 variables, then it's no longer bivariate. It's something else, multivariable or multivariate, as the case might be. Then in multivariable analysis, we're looking at 3 or more variables. So for example, we might say, what is the difference in the mean value of X between groups Y and Z after holding A, B, and C constants? So I'm sure you have all read papers where they say holding something constant or controlling for X, Y, and Z, or adjusting for X, Y, and Z. Whenever you see those terms, they're talking about multivariable analysis. So whenever you hear any term like holding something and something constant, or adjusting for something and something, or controlling for something and something, all of those terms are describing multivariable analysis. So let's talk a little more about regression so that we're all on the same page, so that when we start interpreting the results, they make sense to us. So what does regression mean? When you say somebody's somebody is regressing, what does that mean? Who wants to describe it for us? When you say something is regressing, what does it mean exactly? To regress. And we don't mean the scientific meaning, just the usual everyday language meaning.
Okay, it means to reduce, maybe in price. Yeah.
To reduce. Okay, what other word can we use for it? What other synonym can we place for regress?
Okay, to shrink.
To shrink, okay. What else?
Reduce, shrink, decrease.
Okay, to decrease. That's also correct.
To go back.
To go back. That is it. Now, those other ones were correct, but that is the one I just wanted to, because the question is, why is it reducing? It's reducing because it's going back, right? That is the bottom line of what we want to focus on. Regression is all about going back, right? We're going back and back and back. That's why it's reducing. That's why it's shrinking. Why is it shrinking? Well, it's because we're going back, right? So we need to understand these things from first principles. Regression analysis is all about going back. We're stepping backwards. Now, the question is, why are we stepping backwards? Why are we going back? Any thoughts? Because if we don't understand it, then we just use those terms without really understanding what we're talking about.
Udofia.
Okay. So in my own words, I think we are actually going back to actually find out what happened before now, in my own simple way of interpreting it.
Oh, I see the context in which you are using going back. It's like, oh, we are like doing a post-mortem analysis. We're going back to say, oh, let's go and investigate. All right. But going back in this case, I meant like literally, we're taking a step back. We're not going back in time. We're staying still at that point, but taking a few steps backwards. All right, let's give an illustration so that we're all on the same page. So, if you've heard a saying that, oh, one cannot see the forest for the trees, right? If you're standing right next to this tree, you can only see the tree, but what can't you see? You can see the tree, but what is it that you cannot see?
Yourself. Okay. Emmanuel.
We can't see the forest.
Excellent. Right? Now, the question is, do I want to see the forest or do I want to see the tree? Who is the only person that can answer that question?
Myself.
Excellent. So if my interest is to see the tree, what should I do? And if my interest is to see the forest, what do I have to do?
You have to call down the tree.
Oh, well, let's be conservationists here, okay? Let's not cut down any trees. But if I want to see the tree, what do I need to do? Versus if I want to see the forest, what do I need to do?
Wisdom.
You go closer. If you want to see the tree, only go closer. But if you want to see the forest, you go far back.
Excellent. That's it. In other words, if you want to see the forest, can you reframe your answer and say, if you want to see the forest, what do we have to do? Use the special word we have of interest. What's the R word we're looking for? Regress. Exactly. If we want to see the forest, the whole forest, we don't care about the tree now. We want to see the whole forest, we have to regress. And we established that regression means just take a step backward. Don't stay so close to the tree. If you stay so close to the tree, you're only going to see the tree. But if you want to see the whole forest and all its patterns, then you can't stay so close to the tree, right? But by moving far away, what can't we see anymore? And we are fine with it. What if we take a step backward, what is it that we can't see again? because we need to
Yes,
understand trade-offs.
Yes, you can mute. All right.
Might not be, if we move too backward, might not see the tree clearly again.
Excellent. Now, again, we said that the only person who can determine what they want to see is us. And it's fine, right? We can say, well, I'm not so interested in this particular tree and the color of the bark and all of those things. I just want to see the big picture of the whole forest. So we are the ones who determine whether it is the tree we want to see or the forest that we want to see, right? And that's fine. If we want to see the single tree, we can do a univariate analysis of that tree and describe, this single tree, it is so tall, and the bark is so and so. That is a univariate analysis, looking at that single variable. But if you want to see the whole forest, well, we got to step back from that tree. That allows us to see the big picture, right? Now we've stepped backwards. Now we can see the whole forest. I'm like, oh, wow. There are actually so many colors to this forest. Like things that we will not be able to see if we're standing so close to that tree. We can now see that, oh, wow, there are actually some trees that have green leaves, that some have yellowish leaves, that some that have purplish leaves. Those are things we will not be able to appreciate if we're standing close to an individual tree. But now we can see them because we have stepped away from a tree. So instead of doing a univariate analysis of a single tree, we have stepped backwards to see patterns, not just individual tree, but patterns in the overall forest. So we can see, wow, in this section, now we can see that maybe there are patterns by section, that in this particular section of the forest is all green, and then there are some sections, but whenever there are yellow, whenever you see one yellow, it's also always accompanied by a stretch of yellows, right? And then whenever you see purplish, they're always occurring in a spiral. Those are patterns that we can only see by stepping back, or in other words, by regressing, right? And that's why we do regression analysis. We step away from individual data points, not that we don't care about those individual data points, but because we want to see patterns and not necessarily describe that particular individual. We don't care about Mr. Sampson in row number 41. We want to see the overall big patterns that emerge from the data. The same thing, of course, with, has anyone here seen the Earth? Like the full globe? This is a paradox, right? We're standing right on the Earth. But has anyone ever seen the Earth with their two eyes? I mean, I don't mean in pictures. Any thoughts? If we are on the Earth, when I was little boy, I actually used to think we are inside the Earth. Took me a while to realize that we are on the Earth. So if we're standing
No one has seen the Earth.
Sorry?
The answer is no. No one.
And why? If we're standing on the Earth, why can't we see it?
Because it's so close to us.
Exactly. We're too close. So for us to be able to see the Earth, what do we have to do?
You have to regress.
Excellent. You use the exact word right off the bat. So we have to regress from the Earth. We have to take a step back, or many, many steps back. We have to actually go into space so that we can take a whole lot of steps back and then look and say, oh, wow, now we can see the patterns, right? The same thing with this proverb about an elephant. You have a bunch of blind men who were asked to touch an elephant and describe what they saw. So one says, oh, it's a rope. The other one says a wall, and so on and so forth. And the reason is because they're starting so close. If only they step back, then they can say, oh, this is an elephant, in all its shape. So that is why we do regression. Now, in regression analysis, we say we control for things. So before we go on to our interpretation, we need to understand that part of the picture too. What do we mean when we control for something? Well, if you've ever taken, a flight, the pilots will always say, everybody should sit down and put on their safety belts. Only the flight attendant is allowed to walk down the aisle. That is exactly what controlling means. It means every other person, we only want to see one person, the person in action, and everybody else has to sit down and, sit down in a constant position, right? So when we say that we're looking at the effect of age, controlling for gender and race, we mean that gender and race must sit in their seats and must strap on their belts and must not do anything. So they are as good as sleeping or good as dead, right? The only thing that matters at that point is the variable that we're looking at. So that's what we mean controlling for. It means that, you know, we hold that variable constant. So let's say that, let's go back to this variable here. So here we say sex, the reference is male. So when we say that we're holding sex constant, what that means is that everybody in the analysis automatically becomes what? If we say we're holding sex constant, it means everybody in our population in the analysis becomes what? Jeremiah, your hand is up.
Jeremiah, you can mute.
Okay, it means everybody becomes unimportant.
Okay, they're important, but we said controlling for means we're putting them in their seats and we're holding them constant. Everybody, they're not, you know, they are muted in terms of their impact. Now, look at this table here, right? Sex, the reference group is male. So if somebody told you that analysis controlled for age, for gender, what does that mean in practice? It means that everybody in that population becomes what as far as gender?
Shamsuddin.
So everyone in the population now becomes male.
Excellent. That is why we choose reference categories. So when you do a regression analysis and you say, I'm going to use gender as my reference group, what that means in practice is that when we are holding everybody, when we're holding gender constant, it means, oh, everybody is treated as male. So if everybody is treated as male, what then does that mean as far as gender as a confounder? Will gender be able to explain any differences that we are seeing if everybody is the same gender? Does that make sense? Because you should be able to understand what it means by saying we're going to treat everybody as male and the implications that have for our results. So if everybody's male, what does that mean then?
Manuel.
Yeah, Prof, I think what it means is that gender will be able to account for any change you are seeing there.
Okay. While I have you on the line, if we hold everybody as male, is gender still a variable of interest? Yes or no?
No.
Why? For something to be a variable, it must do what?
It must have an influence.
Okay. Listen carefully to the words. For something to be a variable, it must what?
It must vary.
Excellent. So if we hold everybody as male, it means that gender is no longer what?
A variable.
So if it's not a variable, can it influence the result?
No.
No, it can't. So that means that when we hold gender constant and everybody is male, it means that the gender can no longer influence our result. So that means that we have completely muted the impact of gender on the result. Does that make sense?
Yes, sir.
So that's why when we're doing the results, if we say that we're looking at the impact of, let's say, school level, controlling for sex and race and time to this and all these other variables, it means that for all the other variables, we are holding them constant at the level of a reference group, so that they are no longer variables that can influence our results. So that as far as the results are concerned, the only thing we're looking at is that variable we're interpreting at that moment, right? It's like this picture here, where the only person in question is the air hostess. Everybody else is seated. So if the air hostess falls, she can't actually blame anybody and say, oh, you know, it's like it's completely on you at that point. Nobody was interfering with you. You were the only person in action. Do we get that right? Okay. I'll take that as you know, that's clear. That's clear. So we need to be able to. So the point we're going over this in painstaking detail is that we need to be able to. It's not enough to just plug in some numbers and some outputs and then get some results. We need to be able to interpret what we have seen, we've gotten, and make sense of it from a very basic intuitive level. All right. Now we'll finally come to our results for our interpretation now. So how do we interpret results from odds ratios? Now, when you're interpreting your results, you want to make sure that you look at the confidence interval. The confidence interval should not contain the null value. If it contains the null value, it means that the result is not statistically significant. The null value is 1 when we have ratios. Think of a ratio as x over y. Well, if the two numbers are the same, x over y equals 1. That means that 1 is a null value. Null means that it has no impact. So when you're looking at the results, look at the confidence interval. So when you're presented with odds ratios, the first thing you want to look at the confidence intervals and see whether they contain the null value, which is 1. If they contain the null value, it means that your results are not statistically significant. Right? So that's the first thing you want to do. Odds ratios that are bigger than 1 tells you that the relationship in question is positive. So in other words, the odds increase as the exposure levels increase. Odds ratios that are smaller than 1 tells you that the relationship is inverse, or it's protective. So in other words, the odds reduce with increasing levels of the exposure. So we need to be able to understand this. So in this case now, can we say that these odds ratios are statistically significant? Let's start with baby steps. So baby step number 1. Is this confidence interval indicative of a significant relationship? Yes or no?
Manuel, Andrew.
Oh, sorry, I was just raising up my hand because I didn't get something you said clearly about the confidence interval. Yeah.
Okay. Is there a question in there?
Yes, you're saying you didn't get what you said about confidence interval. But
Yes, so what's exactly the question? What exactly is the question?
Manuel, what's the question, please?
Okay, you started saying that when we are looking at our confidence interval, there's a null value, and which is 1, right? So I didn't quite get the interpretation when we have a null value of 1.
Okay, so we say we're going to take baby steps, and baby step number 1 was to say, when you are presented with odds ratios, first thing first, look at the confidence intervals. This is the part here. The confidence interval, if it contains the null value, it means that it is not significant. And this should be intuitive to us, right? If you have a kid and the kid is in company of guys who are like very sketchy, it's like, if like show me your friends and I'll tell you who you are, or however they say it. So if the confidence interval is in company of the null value, that means it is null itself. So the null value is 1 for ratios, right? So a ratio is 1 number at the top divided by 1 number at the bottom. 2 divided by 2 is 1. So if the number at the top and the number at the bottom are the same, that means that, well, that is, the ratio of them will be 1. So 1 is the null value for all ratios, whether it's risk ratio or odds ratios or rate ratios or whatever ratio. 1 is a null value. So if your confidence interval includes 1, it means that your result is not statistically significant. So you should not be there waiting for someone to come and give you a p-value before you can interpret the result. You should be able to look at the result and say, oh, I can see that the confidence interval does not include 1. Now, from what you can see here, Does this confidence interval include 1? And I'm specifically asking the person who asked the last question.
Okay. Yes, it includes 1.
So what will be your conclusion?
It's not significant.
Yeah, it is not statistically. Always try to put that word statistically because there are different kinds of significance. So it is not statistically significant, right? What if I were to change this to this? What will your interpretation be now?
Okay. It's not up to 1, so it is statistically significant.
Okay. So so again, the emphasis should be on, does it include 1, right? If it includes 1, so it's not so much about whether it's up to 1, because it could be more than 1 in another context. The real issue on hand is, does that confidence interval include 1 or not? All right. So great job. I hope you're clear now, Andrew.
Yes, sir.
All right, awesome. So let's cancel this back to where it was. All right. Now, there are 2 ways you can interpret the odds ratios. You can choose to interpret it on a multiplicative scale, or you can choose to interpret it on a relative scale, right? On an additive scale. So here we can say, for example, we can just, in other words, a simpler way of saying that is to say, we can interpret it exactly the way it is, or we can even simplify the interpretation further. Now, who wants to take a stab at interpreting this? And this is a trick question. I want to catch somebody who will use the banned words we've said earlier in painstaking detail. So who wants to interpret these results for us and make sure they use only the words that are approved? I'm sure you all know the words that we've disapproved of at the very beginning.
Kenneth?
Oh, I'm showing the results already. That is so funny. All right. So please go ahead.
Yes, so Prof, there is 50% lower odds, or there's 50% or 0.5 lower odds.
Okay. So the outcome here is cigarette smoking, and we're comparing, the reference group is males. So this result are done for females. So can you say out the full sentence, please?
Yes, please. So as compared to males, females have 50% lower odds of smoking cigarettes.
Okay. And is that association significant?
Yeah, hello, Prof.
Yes, go ahead.
Yes, please. So I said, as compared to males, females have 50% lower odds of smoking cigarettes.
Okay. But you have only used the information here. You've not told us, you must use the information from both sides of the table, here and here. So your statement is still incomplete.
All right.
You want to complete it? However, so let's put a transitive word there. However, complete the sentence.
Just drop off.
Somebody else then.
Eventually you can unmute.
Thank you, sir. Yes, sir. Please, will you please come over the question again? I was a little bit distracted with something.
Oh, I thought you raised your hand.
Yes, sir, I did earlier, but something came up along the way.
Okay, we
Yes,
said interpret the results.
Oh, okay.
result, I will interpret the results as compared to male or relative to male, female has 50% less odds of smoking, and looking at the 95% confidence interval that include the no value of 1, it therefore means that the differences between the habit of smoking between male and female is statistically not significant.
Thank you very much. Now, I want somebody to interpret it with the wrong words. Those are banned words, so that we all know how not to say it. The interpretation should be technically correct, but use those words that we are completely said are no, just so that we are all on the same page what not to do. So who wants to take a stab at this? This is now negative reinforcement now.
Samson.
All right, so compared to group B, and there was 50% higher reduced likelihood of cigarette smoking among group A, but this was not statistically significant.
Excellent. So why is that sentence technically wrong? So that we're all on the same page.
Okay, so we are dealing with odds. And then when dealing with odds, we don't use likelihood or probability again, because
Excellent.
it's a ratio of 2 probabilities, so they cancel out.
Excellent. Very good. Who wants to take a stab at explaining this? Again, we're talking about smoking. We're comparing males, females with men as the reference group.
Maurice, you can unmute. Okay. Emmanuel. Zachariah.
All right, let me give you the title. According to the statistical data, females are 40% are having 40% odds of not smoking, and the result is statistically not significant due to the 95% CL level.
Okay, but why do you say it's not significant? If I might ask, what's your argument? Like what drives to that conclusion?
Well, because 0.6 actually falls between the filter interval of 0.1 to 0.9, but it's not past 0.9.
Okay. Thank you for your effort. Does somebody wants to help us out? Do we have any helper?
Yes, I want to contribute.
All right, thanks, Pius. Go ahead.
Okay, so among females, the odds of self-reported current cigarette smoking is 40%. The odds of self-reported current cigarette smoking among females is 40% lower compared to males, and this finding is statistically significant.
Thank you. Can you help us with the argument for why it is significant, so that we don't just want to ignore that previous arguments made. We want to make sure we correct before we leave it.
Okay, sir. So the confidence interval, it's on the left side of the null. That is both the lower and upper bounds of the confidence interval does not contain 1, which is the null value. So if it had 1 or crossed 1, then we say that this finding is not statistically significant.
Excellent. Thank you very much. So that's correct. So we can say, females have 0.6 times lower odds. If we're just interpreting the way it is, we use the word times. So 0.6 times lower odds of being current smokers compared to male, and the result is significant. Or we can say that females have 40% lower odds of being current smokers compared to male, and again, the result is significant. All right, who wants to take a stab at this? Again, we're comparing the results among females compared to men, and the outcome is still the same, current cigarette smoking.
Kelvin.
I actually have a question. Why is this significant when we have, okay, not this one, the last one, please, the last slides. Okay, why is this significant when we have one? The confidence interval contains one.
How does it, can you explain how you are perceiving it to contain one, please?
Okay, we say when the confidence interval has one, it is statistically not significant.
Yes, that's
how.
what
Yes, but in this result, the odd ratio is 0.6, and the confidence interval has one at the middle.
I'm trying to understand how does it include one in how you are looking at it? Can you explain to us how in your worldview it includes
0.1. Okay, I think whenever the confidence interval has one among the figures, it is not significant.
That is correct. That part of the argument, we don't have any fight with it. What we're trying to understand is how do you deduce that this confidence interval includes one? That's what we're interested in. We're not interested in the premise of the argument, but in your conclusion. How do you conclude that this confidence interval includes one?
We have 0.10 here. So
okay.
0.9, yes.
Okay.
So in this case, I will say it is not significant because it includes one.
Okay. How you have not answered, you have not made a case for why you believe it includes one. You have just declared that it includes one, but you've not presented a clear argument for why you believe in it. So, okay, let's count, right, from a number line. We start from 0. What comes after 0.99?
1.
Okay, so is 1 included in this range?
Okay, if I'm talking for the left, 1 is not included. But if I'm talking when you are going towards the right, there is 1. No, towards the left, there is 1.
How? How exactly?
Prof, I think what is
I don't
looking
know
at
if
the
you get me, sir.
appearance, just the number like 1, not the value. The appearance of the number 1, that's what he is.
Okay,
he is
Kelvin, are you confused by this 1 you are seeing here?
Exactly.
Is that what you're confused by? Kelvin, are you still with us? Okay, we've lost him. Okay. When we say 1, we mean 1.0. We don't mean 0.1. We don't mean 1 being a digit in some other number. We mean the whole number 1.0. Are we all on the same page? Kelvin, are you still here? I want to make sure that you understand clearly.
Kelvin, you can put up your hand so I can unmute you.
All right, we've lost him. But no, this does not include 1 because we are saying we're counting along the number line. And please, don't confuse the appearance of 1 in another number to mean it's 1. We mean 1.0. That's what the null value. This is not 1. This is 0.1, which is very different from 1.0. So let's all be clear about that.
Okay, sir. I understand now. Thank you so much.
Oh, you're welcome. All righty. All right, okay, this is the one we were on before. Who wants to take a stab at explaining this?
Okay. Igbe Kelly.
Okay, thank you, Prof.
Okay.
Yeah, thank you, sir. Yeah, comparing group A with group B, I would say that group A has 1.60 times the odds of self-reported current cigarette smoking. And looking at the confidence interval, it is that the difference between the two group A compared to B, is statistically insignificant because it contains the known value of 1. And on the other side, I can also interpret it as comparing group A with group B. Group A has 60% higher odds of self-reported current cigarette smoking, and the difference is statistically insignificant
Okay,
because
thank you. Okay. So the only way you're absolutely correct. The only things I will encourage is, one, you should learn to say present results in a more concise way. So say with fewer words. Then when you're saying things that are contrasts, try to use the words but or however, not the word and. When you say and, it means that you are building on something, an argument that is consistent. So when you say the odds were 1.60 and the results were, no, that's kind of confusing. So you say 1.60, however, now that tells you that you are contrasting something that is on the opposite. However, the results were not significant. So, but your argument is completely fine. Your explanation of it was right. We just want to learn to present our results more concisely and use the right transition words. All right, who wants to present this? Now we're trying to look at both the scientific accuracy and how concise you present your results. So all of those things must be packaged together. Who wants to explain this one for us?
Emmanuel.
So, Prof, I will say here, the odd of A when compared to B, self-reporting current cigarette smoking is 2.6 times greater. However, it is not statistically significant because it included 1.
Okay, I think we have this problem about this one that we need to really clarify before we leave this class. How does it include 1 in your worldview? What do you, I'm trying to understand how you see it and how you conclude it includes 1. So maybe we should try and understand.
Oh, sorry, Prof. It is significant, sorry.
Okay, all right.
It's greater than 1.
Exactly.
Yeah.
I was really, really confused. I'm like, okay. Like, I was just curious how you guys seen it and making you conclude that yes, it's 1 included. All right, thank you. Okay. So if we were to express it as a percentage, how could we express it? If we didn't want to say 2.6 times higher odds, if we want to express as a percentage, how could we express it?
Decalen. Udofia. Udofia, you can unmute.
Yeah, okay. For me, based on this data, people of group A have 2.6 higher odds of cigarette smoking as compared to group B, and that actually accounts for about 60% higher odds, and it is statistically significant.
How do you come with First of all, let me correct two things. You're right, like generally the first part of a sentence. But when you say 2.6, make sure you include the word times. So it's not just saying 2.6 odds, 2.6 times. So that word, don't just swallow that word, okay? Make sure you enunciate it. 2.6 times higher odds, you know. Now you said another way of saying it is that it's 60%. Why? How did you come up with the 60%?
Okay, so I actually look at the confidence interval of between 1.99 to 3.5. So if this is actually 2.6, so I'm just looking at it being between 1.99 and 3.54.
Okay.
I don't know if I'm correct. Yeah.
No, you're not correct. You're correct the first one, but not when we want to express it as a percentage. Who wants to help us out in that regard?
I think I saw an answer here.
Dr. Eric.
Yeah, so I tried. So individuals in group A had 160% higher odds of being current smokers compared to individuals in group B. And this association is statistically significant.
Excellent. So you subtract 1 from the number at the front, right? In the initial one, when we had 1.60, well, we subtracted 1 from 1, that left 60. Well, in this case, when we subtract 1 from 2, we're left with 160. If this were, let's say, 5 from, okay, who will interpret this one for us now? Now it's no longer 2.60, it's now 5.60. How will you interpret this?
Moses.
Individuals in group A have 5.6 times higher odds of being current cigarette smoking, and this result is statistically significant.
Excellent. Or we can frame it as what?
The main challenge for Spider is to find out.
Okay. Who wants to help us with the second explanation, which is where we're even more interested in the second part?
To them?
Yeah, so you will say that it is 60%, they are 60% more likely to get the outcome, and this is significant.
Okay, thank you. What happened to the number in front? Remember what we said? We said what's the process for describing or explaining the result? You take that number and then you subtract what? Sedam, are you still on the line? You just said 60%. You completely ignored every other thing that was here. We need to really reinforce that part of the explanation. That is extremely important. Who wants to help us clearly, not just give us the answer, but walk us step by step so that we are all on the same page? And please, we should all listen carefully. Who is confident of the answer to just reinforce it positively for us?
Inshallah. Inshallah, you can mute.
Can you hear me?
Yes.
Yeah. So the odds, the individuals in group A have 5.6 times higher odd of being self-reported current cigarette smoker compared with the individuals in group B.
Okay, thank you. That's correct.
That translates to 460% higher odds among the individuals in group A compared with the individuals in group B.
Thank you.
And this is statistically significant.
Can you please walk us through the calculation? Because we seem to just be swallowing the number in the front and just reporting 60%. That is wrong. So please, can you just walk us how you came up with that number so we're all on the same page?
Yeah, we deduct 1 from 5.60. It gives us 4.60. Then we multiply 4.60 by 100%. That gives 460%.
Excellent. All right. So I think we've covered that enough. So please don't just drop the number in front. It is part of it, because for those of us who answered 60%, it's like you are completely ignoring this huge big number in front of you and you're just focusing on the float. You have to include both numbers in interpretation. All right. The do's and don'ts: use the 1, 2, 3 rule for decimal places. Like we said, 1 for percentages, 2 for odds ratios or other measures of association, and 3 for p-values. Always indicate the comparator. Don't just describe results and don't tell us what you're comparing the results to. If you had a choice over p-values and confidence intervals, always report the confidence intervals, and the p-values are less important. If you give me confidence interval, I can calculate a p-value, right? So I don't need you displaying the p-value in addition to the confidence interval. So the confidence intervals are more than enough. You should show odds, the crude and adjusted odds ratios as required by the Strobe documentation. Now, the don't use odds ratios for common outcomes. You should use prevalence ratios, which are more conservative. Avoid saying things like almost significant. Remember that statistical significance is like pregnancy. It's either you're pregnant or not. There is no such thing as almost pregnant. Don't use terms that suggest causality, and don't show only p-values, right? Here, I have a table, a manuscript that we just wanted to highlight some of those things. I showed this briefly last week, but I just want to reinforce some of those elements again. So here, look at this section here. Factors that were associated with malaria AKI death included acidosis. Like, what does that mean exactly? What's the reference group? There's no indication here, right? That is a no-no. Always indicate the reference group. If you are looking at per unit increase, tell us so that we know what the benchmark is. Don't just say the following factors were associated. We don't know what you're comparing with. That's a hard no. Don't be inconsistent. So you see here, the odds ratios, this is 7.0. Then you have, this is 1 decimal place. And then some, you are having 3 decimal places, 671. This is a whole lot of inconsistency in this paper, right? Then in some cases here, you have this, 14.4. The confidence intervals are from 3.0 to 66.9. Obviously, that tells you that the sample size was very small. And so that's why you have very wide confidence intervals. So these are some of the things that we want to pay close attention to. Here you have a valid negative numbers, like we said earlier. In such cases, if you're going to describe mean values, you want to make sure that you avoid using dash for things that have negative values, because that can then be very confusing. So then you should also be able to know how to use, on last note, before we close the class, how to use these odds ratios when you are also like calculating sample size. When calculating sample size, you can use odds ratios or prevalence ratios as measures of effect size. And I'll quickly demonstrate that before we call an end to our class, very briefly. So let me quickly demonstrate that. So if you're calculating sample size and you want to know, okay, I want an odds ratio, I want to detect a minimum odds ratio of, let's say, 1.5, right? You can absolutely use your odds ratios as the measure of effect size, or in other words, the minimum difference you want to detect. So let's say you're trying to do a cohort study or a case control study, and you're trying to say, okay, I want to set an effect size which my study should capture at a minimum. There are many options available to you in terms of what you can use as measure of effect size. Effect size simply means what is the minimum difference between group 1 and group 2 that I want to detect. So that's what we call effect size. So let's show an example. So we're doing, let's say, a cohort study, or let's say a case control study. The first thing you always have to provide an effect size. And first, before you even do that, you need to provide a prevalence of outcome among control group. So for comparative studies, those are the two most important parameters that you must specify when calculating sample size. Number one, what is the control rate? In other words, you have to set the goalpost. What is the goalpost, right? The goalpost is the burden of a disease among the control group. There is a reason why we have control group. And there's a reason why we call them the control group, because they set the benchmark. So you have to set the prevalence of the outcome among that benchmark first. So here we can say that, let's say the prevalence is 20. If you don't know the prevalence among the control group, you can put the prevalence in the general population, right? That is why we have controls. Now, for this part here, you have a lot of options. We provided a lot of options for you to define what the effect size might be. What we want to focus on today is odds ratios or prevalence ratios, right? You can use odds ratios if you want to, and the reason for providing this is because, well, researchers think in terms of odds ratios. So there's no point forcing you to come and think in terms of prevalence when you can think in terms of odds. So I can say, okay, I want to detect at minimum an odds ratio of 1.5, right? You can't say I want to detect an odds ratio of 1. That does not make any sense because 1 is a null value. So there's nothing to detect there. So you can say, okay, I want to detect an odds ratio of 1.5 for my study at a level of 95% confidence interval. I want it to be a two-sided test, obviously. Two-sided test is what you should use as a gold standard. I have a power of 90%. The ratio of controls to cases is 1. And I expect a 50% response rate among participants. If I set this and calculate it, it gives me that I need 99 cases and I need 99 controls. You should know from first principles that the smaller the effect I want to detect, the larger the sample size I will need. So if I said, okay, I don't want an odds ratio of 1.5, I want to detect an odds ratio of as small as 1.2, no one needs to tell me that this will increase my sample size, right? It's going to absolutely increase. Now I need 98, 196. But if I make the effect size larger, 2, for example, the sample size will decrease because now I'm trying to, let's put this. So recognize that the different parameters here, you should absolutely try and play with the different parameters and see how they affect sample size. So for example, changing the power to 80 and the test from one-sided to two-sided, the impact that has on the effect size. You should also know the difference between odds ratios and prevalence ratios in terms of the level of conservativeness, in terms of the results, right? So these are some of the things that you should absolutely play with as ways of familiarizing yourself with the results and seeing how do certain parameters influence the results, and how can we account for those things when we're calculating our sample size. You should also be able to know the things that will trigger errors and the things that do not make sense. So if I said, for example, a prevalence of outcome among control group of 20, and I say the prevalence of the outcome among the cases is also 20, right? And I try to get results, obviously that makes no sense, right? Because that is the same thing as saying that I want to detect an odd, a difference of null difference. Like, why are you doing the study then? The same thing with odds ratios here of, if I want to say, of 1, then that makes no sense either because I'm trying to detect the null value. It makes no sense because I need to be able to detect some difference in my results for it to make sense, So my encouragement to you will be to say, try and see how changing certain parameters would affect the sample size, and see, and play with that and say, for example, how does changing from a one-sided test to a two-sided test, how does that influence sample size? So for example, if I have a prevalence of 20 among the control group, and I set my odds ratios, the minimum odds ratios I want to detect as 1.5, and I have a two-sided test, right? And I then change that to a one-sided test. So now I have 148. Now I have 116, right? Why would that be dangerous for me, right? From first principles, why would having a switch from a two-sided test to a one-sided test, sure, it gives me a smaller sample size, but why is that not necessarily a good thing, right? Those are some of the things that we need to understand just from first principles so that we can, we have a good understanding of what we're doing. And it's not just about plugging some numbers into a formula and getting results. We can understand and interpret what all of those things mean. You should also be able to familiarize yourself with the difference between odds and prevalence ratios, and how those differences matter when we are calculating, sample sizes, or in general, when we're talking in general, how will that matter? How does that matter in the grand scheme of things? But if we're unsure, we can just stick with what we know. That's why we have many options here. We can just stick with what we know, like the odds ratios, and then just go from there. All right. If there are any questions now, I'll take them.
Thank you, Paul, for this lecture. Eric Yadom.
Please, I want to ask a question about case control. I mean, the sample size calculation. Because when we were projecting it now, I saw like what we were doing over there was 1:1 and match case control. So what if I want to do like 1:2? How am I going to calculate for the sample size using what you just projected to for us to see? Thank you.
Okay, sure. So if you're going to match, so let me share my screen. That the principle is exactly the same. So in that case, you'll select from here. So you'll have a case control study. The prevalence of outcome among the control group will be the same. Let's say I want to detect an odds ratio of 2 at the minimum in my study. Then here, of course, like we said, always use a two-sided test, always. A two-sided test means that I am willing, I believe the result will go this way, but I am open to the possibility that it could go the other way. So I'm going to provide enough room in my study that it will be able to test this way as well as that way. That's what a two-sided test means. A one-sided test means that I think the results will go this way, and I am very close-minded. I am not willing to open my mind to the possibility that the results could go the other way. So I am willing to die on this hill that it is this way or no other way. As you can agree, that is not a very reasonable way to go through life or through research, right? So always go for a two-sided test. You set the power, and you should also be able to understand immediately the relationship between the power and the type 2, error we discussed. Power of 80 means that you have the probability of the type 2 error is 20 or 0.2, because the power equals 1 minus beta. Beta is type 2 error. Those are things that should be very familiar to you by now. To answer your question, if the issue of the controls, you simply specify the ratio you want here. So if you want a ratio of 2:1, you just put 2 there and you click on get results. So now you need 56 cases and 112 controls. Now note that beyond 4, we always recommend in epidemiology that the maximum ratio you should set should be 4. Now, it's not that if you set 5, you won't get an answer, obviously not. But at 5 and above, the juice is no longer worth the squeeze, right? Remember that for each person you are recruiting in your study, you need to spend money and time to recruit them. At 5 and above, the effort or the results we get from recruiting more and more people begins to fade, right? So we don't get so much, so much results for every ounce of effort we put into it. And so that's why we recommend that your ratios should not be more than 4, because that's where we maximize the efficiency. All right. I hope that answers the question. Any other question?
Thank you. Dr. Eric, Hussein.
Okay, so thank you very much, Prof, for your insightful presentations. I have three simple questions. The first one, you stated that in reporting the results, we should report the odds ratios and the 95% confidence intervals, and that is enough. What about someone who wants to know how strong this association is? The confidence intervals will be able to determine that there's an association or not. But some epidemiologists or statisticians will want to know whether this association is very strong or not. In the first place, is there anything like strong association? And if yes, is it not necessary to, show that using the p-values? That's one. Two, what informs the choice of the odds ratio in calculating the sample size? If you are designing a case control study, for example, the odds ratio that we assume to use to calculate the sample size, what informed that? Do you have to have a reference citation for the choice of that odds ratio? The last one, you said when the outcome is common, we should consider prevalence ratio instead of odds ratio. Can you please throw more light on that? Thank you.
All right, that's a good question. So, all right, so the first one was about strength of associations. So, yes, there is such a thing as strength of associations. In fact, in Hill's criteria for causality, that is one of the conditions, the strength of association. But where you have gotten it wrong is to assume that the strength of association comes from the p-value. That is where you've gotten it wrong. It does not come from a p-value. Where do we infer the strength of association? Who wants to answer that question for us? If it's not from the p-value, where is it inferred then? Any thoughts?
Moses.
R. The R squared value.
Sorry?
The R squared value.
Okay. Okay, let me share my screen again. Hold on a minute. Share my screen. All right. So let's look at these case studies again. Let's look at case study number 3 and number 4. Number 3 is 1.60. Let's make this significant. 1.99. Let's make this 1.90, and let's make this 1.69. All right. All right, so we have two studies here. We're looking at case study number 3 and case study number 4. Which of this has or let me make it easier for us by putting them together on the same screen. Let me copy this. And let's put it so that we're comparing them easily. Okay, good. So now we have two things on the screen. Remember the question that was raised was, how do we assess the strength of association? Okay, these two results, which one has a stronger association? And how do you determine that?
Emmanuel, would you? Okay. Dr. Emeji.
Thank you very much, Prof. Thank you for the knowledge you are imparting in us. Prof, I want to digress a little. I want to ask whether you can please explain to me. I don't understand. How do you set match? Well, in a research, they say you should age match and set match. What do you mean by those terminologies in research?
We'll come to you later. Let's address the original question.
Okay, Prof.
Okay, maybe you guys can put your hands down. Those that want to answer this question can now put up their hands, so you would ask your question later.
If you want to ask a new question, please put your hand down. We just want to ask only one people want to answer this question. Let's finish one question before we go to the next. I think Igbekele, you want to answer the question for us? Please go ahead.
Igbekele, you can mute now.
Yes, sir. Thank you, sir. So I would let me do the use the direct method first. 5.0 as odd ratio is higher than 1.90. Therefore, 5.06 has a higher strength of association than 1.9. But if I also want to make it plain, I would say the strength of association depends on how far away is the odd ratio from 1. So that could also tell you as in a layman ways how you can determine the strength of association. So the odd ratio can give you an estimate of how strong or the strength of the association. Thank you.
Excellent. So the strength of association is not measured by what? Let's so that we're all on the clear. What are we not using epidemiologically to say this is a strong association versus that one? What is it that we are not using? So that we are all very, very clear and don't go away with any confusion. Foster?
All right. Thank you for the opportunity, Prof. Yeah, so we are not using the p-value to determine the strength of the association. We use the effect estimate size to determine the strength of the association. Thank you.
That's very clear. Thank you very much. So we look at it, if it's how far away, as Igbekele mentioned, how far away is it from a null value, right? Because it could also be an inverse association like 0 point something. So we're looking how far away it is from the null value of 1. The farther away it is, the more strong it is, or the stronger it is. We are not looking at p-values to say this is strong and that one is not strong. So I hope that is extremely clear. So we use the point. So yes, you were right that strength of association, of course, is one of the criteria we use for evaluating causality, but not in the way you are inferring. We use the estimate itself and the how close or how far away they lie from a null estimate. Unfortunately, I have forgotten the other question you asked. So if you know, you can drop it in the chat, and I can answer it. If you still remember it. All right. I'll take the next question then. The next question was about matching. How do we match? All right, so this gentleman asked the question, when we say we are matching in, I'm so bummed I cannot remember the other questions because I think they were very interesting from a learning perspective. But anyway, please, if you're still here and you can still drop your questions in the chat, I'll be happy to answer them because they were quite interesting questions. I just can't remember them. All right. So the next question that was asked was about matching. How do we match? So let's say that we're supposed to match on, let me grab this text here. Oops. All right. So matching. So we are matching by age and gender. So the question was like, we're doing a case control study and we're supposed to match by age and by gender. The gentleman's question is, what exactly does that mean? And how do we do it? All right, let's explain what that means. So let's say we have two categories of age, less than 50 years and 50 years or older, right? That's by age. And by gender, we have male and female genders. So these are the two variables we are matching on. Now, what we'll have to understand is that matching in case control studies is the exact same thing as stratification in survey design. They are exact same thing. They just have different words. And we use them for the exact same reason, which is for efficiency, right? So if you understand stratification in design of complex surveys, surely you will understand matching in the design of case control studies. So what we do is we're going to create unique strata. So age by gender, each of them have 2 categories. So that means that we're going to have 4 strata. Why 4? Because 2 times 2 is 4. The first strata would be less than 50-year-old people who are males who are less than 50 years. That's the first strata. And the second one would be males who are 50 plus years. The third one would be males who are females. Who are less than 50. And the fourth one would be females who are 50 plus. So this is what we do, right? So we have already, so the author said, oh, we want to match by, we're going to match by age and genders. So if you're going to write a software program, for example, to achieve this, so you're going to, or if you're implementing the study, regardless of the scenario, you will know that, okay, we're going to have 4 strata from this 2 variables, because we have 2 categories for age and 2 categories for gender. 2 times 2 is 4. And immediately we're going to create these 4 conditions. So now we are trying to now launch our case control study. We have the first individual comes, who is a case. This guy is a male who is less than 50, right? So we have the case now. Now, when we have a control, the control for that individual must also be a male who is less than 50, right? That is a condition that must be met. So we're going to have in our data set 3 variables that we're creating. One is whether the individual is a case. So this is what our data set was going to look like. Sorry, let me just quickly explain this to you in a way I hope you will understand. All right, my system is hanging up. Okay. So we have the first individual comes who is the case. So let's call this indicator for case or control status, right? So this is the first individual who is a case, right? He comes. So that's the first guy. That's the indicator was male, less than 50 years old, right? And this is ID number 1. Then the second person who is coming as a control, right? The control must be, so if we have the first control who came, the first control was female who is less than 50. We cannot match that person to this person because they don't fall under the same category. We can only match an individual to this individual if they are also males who are less than 50. So the first control comes, they are female less than 50, we cannot match. The second one comes, they are males who are over 50, we cannot match. The third guy comes, they are male who are less than 50. Yes, this is a match. Now we can match this individual to this individual, right? They belong to the same. So in your data set, you must have an indicator that indicates that, okay, this individual and this individual they are a matched pair, right? They belong to group number 1. And that is how we're going to continue with the next. So the next case comes, he is male who is 50 plus years. That's the second set, right? The control for this guy comes. Again, that control must also be a male who is 50 plus. If they are a female, we cannot match because we've already said we're matching by age and gender, right? And then eventually we have a male comes who is 50 plus, And then we can now match, and that's risk set number 2. Now, when you're doing your analysis, it should be obvious to you that these rows are not independent. One of the assumptions for regression modeling is that there's independence. In other words, row number 1 and row number 2 are completely independent. Obviously, in this case of match case control, they're not independent because this guy and these guys are matched. Matched and independent are two opposite words. They belong on very opposite ends of the table. And this is why you cannot use traditional methods of analysis when you have matching being done. This is why when you use matching in case control studies, you must use conditional logistic regression. What conditional logistic regression is doing is that it is analyzing them as, it's taking this variable here, this column. This is a very important column because it tells us that this and these guys are joined at the hip. And when we're analyzing them, we must analyze them as pairs, right? So that's what's happening in your software. Your software is writing an algorithm that takes this indicator and analyzes them as clustered units. It's accounting for clustering by this indicator because it acknowledges that the case and the controls that bear the same number for the indicator are within the same cluster and must be treated as clusters. Otherwise, you will have, you know, the errors of your margins of errors are going to be too narrow. If you analyze these things together and you ignore the matching, what you end up finding is that there is less variability in the sample because obviously they are related. You end up with very narrow confidence intervals, and you end up seeing everything is statistically significant when they are not, because you fail to acknowledge for the fact that you have matching in the study. So when you're writing an algorithm to analyze the data, or if you're writing the software, or if you're writing a script to do something, obviously you should know that you have to account for the clustering that occurs within the matching. So bottom line, if you match, you must stratify the analysis. That's the fundamental rule of matching. I hope that is clear. Next question, please.
Thank you, Prof. Moses?
Okay. Thank you, Prof. I've actually carried this question from the first day. When it comes to calculating sample size, is it viable in ecological survey whereby maybe someone wants to trap rodents and then you're doing a case control study? Is it viable to trap equal number of organisms in maybe 2 different habitats? Thank you.
So yes, sample size calculation is viable don't think of your study as rodents or human beings or chairs. It doesn't really matter. It's the same thing. The things you should be worried about are, 1, where am I getting these individuals or this unit of analysis? Are they occurring independently or are they occurring in clusters? If they're occurring in clusters, obviously you have to account for the clustering that occurs within selection, right? So these are the more important questions that you will be asking. But in terms of whether sample size applies, yes, it does apply. So if let's say you are trying to look at a descriptive analysis of rodents in an ecosystem, right? In this case here, you would, let's see, the exact same principles will apply. Where's the calculation? So here you would say, okay, I want to look at the prevalence of the percentage of rodents that have this disease. There's no difference at all between calculation of sample size for human beings versus for rodents. It's the exact same principle. So if it's a descriptive analysis, you will still say percentage of outcome, level of confidence will still be 95, the prevalence of outcome will be 50. Now, the question now is, are the rodents existing in clusters? Very likely they are, because maybe rodents, maybe they live in, maybe let's say ants. Ants live as colonies where you have, you have a colony of ants. I'm sure I'm not a zoologist, but I will assume that rats also have colonies. Or it's possible that you may be looking at house rats, where house that live in a house are all considered as clusters, right? So they are not just you're not just picking out the rats one by one in the field. They are all clustered together in units. So if you are looking at the rats, rats in a house, well, automatically the house makes up the cluster, because rats in the same house, well, share the same attributes, eat from the same source, maybe they have the same behaviors. So in that case, yes, you are looking at cluster sampling. You have to provide a design effect. You have to provide the number of strata if that applies, and you calculate it. So the sample size, whether you're calculating for rodents or for human beings, does not differ. What you need to think about carefully is about whether there is some degree of clustering in the target population and how you're going to account for that in your sample size.
Okay, just to interrupt a bit, imagine a situation whereby your independent variable is the habitat type. So you have maybe 2 or more habitat types, and you expect that in the habitat will affect the number of rodents that you'll find there. So is it still viable to calculate population size that you want to target?
So in this case, your study is more of an analytical study. It's a comparative study where you're looking at this type of habitat versus that type of habitat. So in that case, what you do is comparative study with 2 arms. So in this case, let's say it's a prospective cohort study where you're trying to follow some rodents and see, okay, how do whatever outcome compare between the 2? So the first thing is, what is the prevalence of an outcome among the non-exposed group or the control group? And what is the prevalence? What do you think is the prevalence among the exposed group? The outcome cannot be number. The outcome of interest cannot be the number of rodents, because that is not necessarily an outcome per se. You are calculating sample size so that you will get the number that will help you determine that outcome.
Yeah.
So you indicate the outcome among the exposed group. Let's say it's like 30%. So you're trying to see what percentage of rodents, for example, have some disease. So you expect that in the first habitat, 30% of them have the disease, and you expect that that percentage will be lower by 10%. So maybe 20% of those in the other habitats have that same disease. You put those values there. The level of confidence, you put that. It's a 2-sided yes. The power desired 80. The ratio of non-exposed to exposed, maybe you want 1 to 1. And the response rate is, 100, well, because you are catching them wherever they are. And then that tells you that you need 295 rodents in the one habitat and 295 in the second habitat, right? That is what you will need to be able to detect the difference. So bottom line is, yes, the sample size calculation will be exactly the same. It is now, for you to determine how you define the habitats, which is no longer an issue of sample size, but an issue of study design.
Okay, thank you so much.
You're welcome.
Costa, you can ask your question. Costa, are you here? All right. Desalegn.
Thanks, Professor. I just acquire a lot of information. I have 2 questions. The first is, in what context we use the forward analysis in case of SPSS? The second is, in multiple variable logistic regression, how can we choose the reference?
Sorry, yeah, I got the second question very well. I'm not sure I got the very first one. Can you please repeat? The second question is about how do you choose the reference category. I didn't get the first one, please.
Okay, the first question is, in SPSS analysis, there is backward analysis and forward analysis.
Okay.
In what context we use the forward analysis?
Okay. So please, you should never use forward analysis. You should never use backward analysis in any context. We are in 2025. Those are completely antiquated ways of analyzing data that do not make any sense, and you should not use them in any context. I hope that is clear. I don't know whether I can make myself any clearer. Research analysis should be driven by a strong intellectual, theoretical framework. When you do forward selection or backward, it's like, oh, I'm just going to dump all these variables into my model, and I'm just going to allow the computer to tell me which ones I should use. Oh, really? So the computer now is now standing for you. That does not make any sense. So please don't use any of those frameworks for analysis, because it doesn't just make any sense. The second question was about how do you choose a reference group? Well, choosing a reference group, there are many things to consider. Number one, what have other people chosen in the past? Because you want to make sure that your study is comparable with other studies, that people can compare what you found versus what other people found. So in a way, it makes sense for you to use a group that other people have been using. That's one consideration. The second consideration is just what makes sense. If I'm looking at exposed versus non-exposed, well, it makes sense that I should use the non-exposed as a reference group, because in terms of interpretation, it's easier for people to interpret positive odds ratios, right? When you give people an inverse odds ratio of like 0.8, they don't even know what to do with themselves. They're like, okay, like the odds were 0.8. It's easier for people to say the odds were 1.45 higher than to interpret it the other way around. So the issue of communication is also very important. How do people interpret results, and what makes more sense for them? That's also a second consideration that you want to bear in mind. And then the third consideration is statistical. The reference group should have a large sample size so that you can have enough power to facilitate comparisons. So those are three things that you want to pay attention to. Which one is more important? Well, it is all contextual. You will make a decision which one works better, but definitely make sure that their statistical considerations are there, that your sample, the reference group doesn't have a sample size of 5. No, that's a no-no. You should have adequate sample size. And then once there's adequate sample size, well, your choice then is to say, alrighty, am I going to just use what other people have used? That makes sense. Or am I just going to forge my own path and I don't care about what other people have used? You can also do that, but at your own risk, right? Because the journal editor or the reviewers might say, well, why are you using this? And if the editors ask you, that is not to say you cannot use it. You just have to defend what you did. So nothing in science is fixed in stone, especially not those kind of things. You have a lot of liberty to decide what you want to do. Just be ready to make a defense of why you went that way. All right, next question.
Thank you, Prof. Yes, sir. So I want to get a clarification on. Okay, please, sir, can you go back to your slide on don'ts and do?
Okay.
The don't and the don't, and the do and the don't, rather. Yeah.
Okay, sure.
So you talked about don't use odds ratios for common outcomes. Use prevalence ratio. So there was a time I was doing something and a professor was telling me I should, instead of using prevalence ratio in observational studies, that I should use prevalence odd ratios. Do you get that? Do you get that statement, sir?
Yeah, I had it.
Yeah. So I was a little bit confused because I look at the prevalence odd ratio is just the same calculation with the normal odd ratio, but I think it's the context that is different. But now looking at what you said here, how can I match the two together? Don't use prevalence ratio, use odd ratio. Don't use prevalence ratio, use prevalence odd ratio. Please, sir, can you elaborate on that? Thank you.
I understand your confusion completely. All right, so let's explain. Let's break it down from first principles. So, remember with the first class we said there are certain things that are tape measures, like proportions, but the same thing applies to odds. Odds are also tape measures. You can use odds for incidence, but you can also use odds for prevalence. So in other words, you can calculate prevalence odds or incidence odds. So in other words, prevalence odds is when you are calculating odds when you are having a prevalence study, right? Like a cross-sectional study. If I conduct a cross-sectional study and I calculate odds, that is odds in the context of a prevalence study. So those are prevalence odds. If I calculate odds in the context of a cohort study, that's not in the cohort study. What I'm getting is incidence, right? So that's another way of saying that these odds are being calculated within the context of a cohort study. I hope let's understand that very clearly first. So in one hand, we're saying in what kind of study that's another way of saying what type of study are you doing? So if I just see prevalence odds, I already automatically know that that is the context of a cross-sectional or incidence odds. That's the context of a cohort study. Now, I hope that part is clear. All right, great. Now, the next part is odds ratio versus prevalence ratios. Take note that the first one was prevalence odds versus incidence odds. We didn't say prevalence odds ratio. That makes no sense. And we didn't say incidence odds ratio. That also doesn't make any sense. We simply said prevalence odds versus incident odds, right? Odds ratios versus prevalence ratios are completely different things. This has less to do with statistical or study design. We have left epidemiology now. Now we're in the realm of data and statistics. So we're now comparing prevalence odds versus odds ratios versus prevalence ratios. Those are very different things. Odds ratios is a ratio of 2 odds. Prevalence ratio is a ratio of 2 prevalences, right? So now there's a mathematical relationship between prevalence and odds, which we gave up here originally. Let's see that. I can find it. Okay, great. Odds equals prevalence over 1 minus prevalence, right? That's the mathematical relationship between the two of them. Now, when the prevalence is very low, the prevalence ratios and the odds ratios are one and the same. We in one of our earlier classes, we shared a calculator that allows you to convert prevalence ratios to odds ratios. We're going to share that formula in that calculator again for those of you who don't have it, so you can play with it. So you will find that when the prevalence is very low, the odds ratios will be the exact same thing as the prevalence ratio. However, as the prevalence starts getting higher, the odds ratios get bigger and bigger and bigger, way higher than what what the corresponding odds. Let me look for that calculator and show you, so that when you're playing with it, you have contexts. Sorry, hold on a minute. If I can find it. There's no guarantee I'll find it, but let me try. So that when you're playing with it, you can have some contexts. Okay, I'll just have to give up on that. And when I find it, I'll share with you. But the point is that prevalence odds versus incidence odds is a very different conversation that has to do with issues of study design. But when I'm talking about odds ratios versus prevalence ratios, those are different things entirely too. So one is talking about ratio of 2 odds, the other is talking about the ratio of 2 prevalences. And the idea is that when the prevalence is low, the prevalence ratio and the odds ratios are one and the same, very similar. It doesn't matter what you use. However, as the prevalence gets larger and larger, you see that the odds ratio gets bigger. I am sure you have seen studies where people report odds ratios of 1,203 and you're like, or 567, very, very large odds ratios. And you're like, how are the odds ratios so big? Well, the odds ratios are so big because the prevalence was very common. And instead of that author using prevalence ratios, they chose to go ahead and use odds ratios, not recognizing that odds ratios will give you very exaggerated results when the prevalence is common. That's why we say that, because in fact, you as the author should feel ridiculous reporting an odds ratio of 700 and something. It's like, really? you yourself should say that this doesn't make much sense, right? So when the result is very common, when the outcome is very common, this is why we recommend you use prevalence ratios over odds ratios. But there is no such thing as a prevalence odds ratio. That makes no sense. You have prevalence ratios or odds ratios, which is a statistical construct, which is ratio of 2 things, ratio of 2 odds or ratio of 2 prevalences. And you should know when to use which. So in general, when we say when the prevalence is common, which is 10% or higher, so if you're looking at a condition that has a prevalence of 10% or more, that tells you that this is the time when you should use prevalence ratios as opposed to odds ratios. I hope the distinction is very clear to you.
Thank you. Ahmed? Ahmed, you can mute and ask your question.
Yes. Hello, Prof. How are you, sir?
I'm fine, thank you.
Yes. So my first question is, I want to know if it's advisable to round up and round off the lower and upper limit of the confidence interval, because on the normal, when you do your analysis, it comes in more than 3 or 4 significant figures. But probably if you do Chisquares statistics or SPSS. That's my first question. And the second question, earlier this year, someone told me when you're doing binary logistic regression in the crude odds ratio, even if, because in the crude odds ratio, you find the significant predictors, then those which are significant, you run them against in the adjusted odds ratio, right? So someone told me, one of my mentors, he told me even if there are instances wherein some predictors are not significant, but since they are significant in other studies, you still have to run them in the adjusted odds ratio. So I've actually been finding a way to verify that information, because I don't see the need if it is factual for you to include insignificant values in the adjusted odds ratio because it's significant in other studies. That's my other question. Another question, I think I've forgotten a bit. Where is this question? Okay, let's just say this one for a start, sir.
Okay. So good. If you can forget your questions, I have every right to forget them too. I'm just joking. All right.
No, I mean, the last question, I actually had 3 questions to ask.
No, that's fine. I'm just teasing you. All right, these are great questions. Your first question was about rounding. Yes, you can round up and down, but your rounding should be based obviously on rules of statistics or rules of data. Don't invent your own rules to round so that it favors you, right? Follow established conventions for rounding. Number 2 is, what should we include variables that are not significant in the model? That's a very, very important question, right? Because it gets to the heart of how do we select variables that should go into our model. The most important factor that should determine variable selection should be subject matter knowledge. So in other words, when you are fitting a regression model, what you should do is to not set up a bivariate analysis. No, you should sit down and construct a DAG. A DAG is a directed acyclic graph. So let me show you what I mean. Let's create a quick DAG here. Okay, great. I have a DAG here. Awesome. So this is the very first step that you want to take. Not go and get SPSS, not go and analyze data. No. The very first thing you should do before trying to create your regression or determine variables that should go into your model is to create a directed acyclic graph. A directed acyclic graph is a visual way where we construct the relationships of interest. You come up with your exposure here. You come up with the outcome on the other hand. So this is the relationship we want to explore. The exposure, how does it relate with the outcome? Now we'll start filling up our DAG. What are the confounders? The confounders are the variables which I know as a subject matter expert that are associated with the exposure and associated with the outcome and do not lie on the causal pathway. Those are the 3 conditions for any variable to be a confounder. It must be independently associated with the exposure, independently associated with the outcome, and must not lie on the causal pathway. So I'm going to list all the confounders, like age or sex or whatever, right? How do I know these things? It's not based on studies, it's based on my knowledge as an expert. My knowledge as an expert is the most important thing when I'm selecting variables, not what the software is telling me, not what other people have said. I am the expert. I am the one who has been doing this. I know this thing. The computer doesn't have context. Of course, definitely not AI. AI also doesn't have context of a subject matter. Now, I can select the confounder, which I know that if I'm maybe a clinician, for example, and I'm looking at a variable that I know for sure meets this requirement. The software might tell me, no, it's not true. AI may tell me that no, it's not true, but no, I have to disregard them because I'm the expert. So this is what the most important factor that comes into selecting variables. Your DAG helps you know which variables to include in your model and which ones not to include in your model. So on the DAG, I'm going to create not just confounders. I also have to list out collinear variables. The collinear variables are variables that are associated with the exposure, but not with the outcome. I'm going to list all of them too on my DAG. And then I also have intermediate variables. Intermediate variables, like confounders, are associated with the exposure and associated with the outcome. But unlike confounders, intermediate variables lie on the causal pathway. So for example, if my study is looking at the relationship between, let's say, physical activity or physical inactivity and diabetes, all right, I could say that, somebody becomes exposed, then they develop obesity, then they have a heart attack or whatever the outcome is. So in this case, obesity is actually a variable that is on the causal pathway between physical activity or physical inactivity and heart attack or stroke. So it should be obvious to me that if I am fitting a regression model as an expert and I now include obesity in the regression model, that doesn't make any sense whatsoever. Because any person who has any idea of that subject should tell you, how come you are including a variable that lies on a causal pathway in your regression? That makes no sense, right? So by fitting the DAG, I can immediately tell which variables are a complete no-no as far as including your regression model, the ones that should be included in the model, the ones that are collinears that you should definitely not include because they just add noise to the model, right? So this is the most important thing. So if you cannot sit down and create a DAG, then maybe you should not fit that model. Because what forward selection or backward selection is saying is that it doesn't account for all of these things, right? Forward selection or backward selection is simply saying, we're just going to carry all the variables in our data sets and just throw them into the computer, and then the computer will tell us what to use. That makes no sense whatsoever. So the most important thing in fitting a regression model is you and your expertise as a subject matter knowledge, sitting down and constructing a DAG and proceeding with that. So yes, of course, there will be some variables that you select here that the computer will tell you that, no, I don't think so. In which case you should tell the computer, okay, between me and you, who is the expert, right? And the answer to that question should then determine how you go proceed. Now, if you're not an expert either, then we have a little problem on our hands, right? Because then you don't know the subject matter enough to even make any decisions. I hope your question is clear now. Ahmed.
Thank you.
All right, next question.
Taru.
Okay, thank you. Thank you so much, Prof. Can you hear me?
Yes, clearly.
Thank you so much for this insightful session. So my question is, okay, basically I'm more into this experimental research in agriculture. My question is on the p-value and the error bars. There are some situations in which a p-value is actually showing significance, a difference, whilst the error bars are actually overlapping. So when we are interpreting our results, are we going to base our interpretation based on p-value and ignore the overlap that we are viewing or observing in the error bars? How do we actually approach that?
Okay. All right. So let me hold on a minute. Let me pull up some that might help you clarify that. Just a sec. I think that ties in very nicely with that. If I can pull it up again. Hold on a minute. I think I should just pull it up. Because I have a case study that aligns very nicely with the question you asked. So I always believe a picture is worth 1,000 words. So let's look at the picture together so that we save ourselves 1,000 words. Hold on a minute. Let's see if I can find this. Okay, yes, I found it. Okay, then I look for the specific question that I want to share. Right. I'm going to share my screen. Okay, so this is just a mock exam I had for one of the specialties in the US. So, but the question that I had created here aligns perfectly with what you asked. So I just wanted to pull that up, and I just administered this exam to them a day ago. So it's fresh off the press. All right. So this is the question I wanted us to consider. Let me expand this. So the graph below shows the meta-analysis results assessing the effectiveness of an intervention. Which of the following inferences is untrue? So you have here the studies are the studies, study a subgroup. These are the results. And here is the visualization of the result. So let's set some clear rules of engagement so that we can understand how to interpret this clearly. When you are looking at this, first of all, you should look at the null value. The line in the middle is the null. And you should look at the number below that null line. If that number is 0, that tells you that you're looking at averages or means, differences in means, right? Or you're looking at results that involve differences, like mean differences. If the number below that line is 1, it means that you're looking at ratios, or a ratio scale, like odds ratios or relative risks or rate ratios. So again, if the null value is 1, you're looking at ratios or in the ratio scale. If the null value is 0, you're looking at mean differences. That's the first thing you want to take note of. Number 2 is once a number crosses that median line, that null value, that result is not significant. So that's the second thing we want to pay attention to. So if it crosses it, it is not significant. If it does not touch the null value, it means it is significant. All right, now, based on that, let's answer those questions. So the question was, which of the following inferences is untrue? So let's look at them one after the other. The first one is Lombard found no significant association. This is Lombard here. This is their line. So the claim is that they found no significant association. Is that a true statement or is that a false statement? I don't know who asked that question. Do you want to answer? Taro, I believe that question was yours. So what do you think? We're going to take step by step. Do you believe that is that statement true? Lombard found no significant association.
It's not true because it's significant because we can see the confidence interval is below 1.
Look at the picture. Remember we said if the confidence interval touches the null value, it means it is not significant.
Oh, okay. Then in that case, that A is not true.
So we can agree that this is not significant, right?
Yeah, exactly.
All right. The second claim was that Pereira found a significant association. So Pereira is the second study here. This is the result. Pereira.
Very true.
It doesn't touch the null value, right?
Yeah.
So it is true.
So it's true.
The D, well, let's keep the D for now, the C for now. The D is the null value is 0. Yes. When we look at here,
yes,
null value is 0.
Exactly.
The last claim is the pooled effect is statistically significant. The pooled effect in the meta-analysis is that last rhomboid that doesn't have whiskers. This is the one here. So when you look at it,
and that's true.
Exactly. It is significant associated. It's statistically significant because it doesn't touch the null line, right?
Exactly.
Now, let's look at this C claim. The effect found by Pereira is significantly stronger than by Rosato. So this is saying this one here is more significant than the third one. So it's saying the claim is that the effect from the second study is significantly stronger than the third study. Now the question is, can we make that conclusion by simply looking at these two?
Definitely not. And even those effects values are almost similar.
Exactly. So the point is that we cannot just look at the overlap and conclude that there's a difference. So this is one of the things we concluded from the first session, right? That you can't just look at overlap and say there's no difference. You need to do more tests, right? So, so as far as eyeballing the results is concerned, that is a conclusion that we cannot make just by looking at the results. We need to do, if you want to make any tests, well, you can definitely do a lot more statistical tests, but it's not a conclusion you can come to by just looking at the results when you have overlap.
Oh, okay. Thank you so much. It's quite clear.
Okay, great.
Thank you. I saw one question in the chat. That should be our last question for today. Let me read it. He said, thank you, Prof. Please, can you put us through how we can determine p-value from the confidence interval?
Okay. So that should be your homework, actually. Your homework is to go and figure out how we can determine confidence intervals from p-value. It should be obvious to you, the hint is, well, I shouldn't even give you any hint. There's a lot of ways you can do that. So your job is to go and figure out, and you could drop your answers in the WhatsApp chats for the group, and we will see. So you can pick any confidence interval of your choice. You can pick any paper and that has a point estimate and the confidence intervals. And from that, your job is to calculate the p-value from that association. The goal is that you should see why it's so unnecessary to say, give me a p-value when somebody has given me the point estimate and the 95% interval. So that's your homework for the day. All right.
Okay. He's asking again, how do we also determine adjusted odd ratios, and how is it related to proved odd ratios?
You cannot tell adjusted odds ratios just by looking at it. You need context. So if you have just an odds ratio, there's no way to know whether it's adjusted or not adjusted. Somebody has to tell you, the person who did the analysis has to tell you that it was adjusted. So it's not something you can tell just by looking at it. Adjusted odds ratios do not wear a special hat saying I'm adjusted. You have to get context for the analysis.
Suddenly we have two hands up. Yes, you can you repeat? You can unmute.
Okay, thank you very much for this very enlightening presentation. I'm sorry, please. My question, I lost network when you're answering it. It's just about for we to go for a binary regression to find the odd ratio for maybe multiple variables. Is it important to just first do a chi-square test, then those that are significant, you can then subject them to a logistic regression? I'm sorry, I think you tried to answer it, but I think I missed my network around that time. Thank you very much.
I said, no, thank you very much. I said you have to, first of all, sit down and create a DAG. So the first step is not to go and start fitting chi-square tests. The first step is to sit down and create a DAG. I already went through what the DAG is. So if you missed that part, you might want to go and watch that section. So, but that will be the first thing you should do before, so that you have a clear idea of what you're doing, because the most important thing in fitting a regression model is not the statistics. It's about what is the theoretical basis for this? What is the theory in this model? So that will be the first and most important thing.
Christopher. Christopher, a minute, please.
Thank you, Prof, for the lecture. Please, in our interpretation, there is a reference to a reference group. I'm just wondering, in using, for example, SPSS, whereby, for example, we want to look at of sex, say male, female, favorable outcome or favorable outcome, and the odd ratio was calculated by the system. So how do we know which is the reference group in that case? Because most of the time, the software give a column for the gender, then a column for outcome, then it generates the odd ratio. So in this case, how do you?
So every software should allow you to set a reference group. If you don't set a reference group, the software automatically picks the lowest group. So the idea is that don't just rely on, I'm not going to put in the data and the computer should just give me out results, but I don't know what the computer did. Because the computer is not the researcher, you are the researcher. So don't just rely on the computer's default options. You should be able to set the options. This is what I want to use as a reference group. And like I said, if you do not set it, the computer sets the reference group for the lowest. So if you have male coded as 0 and female coded as 1, automatically to set males as a reference because male has a value of 0.
Okay, thank you very much.
Yeah, you're welcome.
Yeah, Prof, I may just add that this is more like a postgraduate class, because I'll be following your lectures. I think it's something more than just certificates. I don't know. You were trying to come up with a master program, online program, but the thing will just disappear. I don't know if there's any update on that.
Yeah, we're going through some accreditation exercises. And so once we're done with that, we'll go through with it. But yeah, even our master's program, the idea behind it is not one of, our goal is really to break down science to be understood in a very simple way. So even our postgraduate classes will not appear to you like the regular postgraduate classes, because they will present the same high level information, but in a very simplified way. So our goal is not to, our goal is to really make knowledge accessible in a very simple way. And so right now what we're doing is creating a curriculum and also going through the accreditation process.
Abdul Hamidou.
Thank you very much. Please confirm if I'm audible enough.
You're very audible, Prof.
Thank you. Sorry, Prof, I'm trying to draw you back a little bit. The class is made up of those who are from the epidemiology and those who are just from the social sciences. So just bear with me if I ask this question.
Sure.
On behalf of those on my own side of the story. We do research on health matters, and then there's this health organization that did some intervention in Kano State. So we want to find out if the intervention has been successful. So after listening to your lecture, I become very I don't know, become very disturbed on how we can get the sampling of because the intervention is in 9 local government areas, and the intervention consists of almost 4 categories of under 5 children, lactating mother, pregnant women, and pregnant and lactating mother. So the organization is claiming that it has done a very good job. So we want to find out whether it has done a very good job. So we don't know. I'm a bit confused on is my sampling going to be based on the categories they gave us, or we'll have to use a different yardstick, because the four categories are also a bit different. Some is higher, some is lower. So how do they just give us the sum total? So I don't know how we can be able to get the sampling in this case.
Okay. So first of all, you have to define what the outcome of interest is. So there was an intervention. The intervention is supposed to solve a problem, right? The problem could be anything. The problem could be underage literacy. The outcome could be dropout of students from schools, or it could be
it is specific. The
okay,
problem is malnutrition among under 5 children.
Okay.
Then breastfeeding among lactating mothers. Then lactating mothers and pregnant women. There's some are lactating and they are pregnant. So their health condition.
Okay. So your problem here is that you don't have, it's not one population. So what you have to conduct is not just one study, but a series of different studies, because you cannot compare apples and oranges.
Exactly.
On the one hand, you have lactating mothers, and the intervention is aimed at these mothers and their own welfare. On the other hand, you have the children on the 5 issues. Children, now the other interventions are directed at children. So you cannot necessarily directly compare outcomes that are related to children with those directed at the mothers. So in other words, your study is now not just one large study, but you have 3 different populations. Population number 1 is a study looking at health outcomes among, children who receive the intervention, and you're going to compare that with another another population that did not receive intervention. This is what we call a quasi-experiment, right? A quasi-experiment is a study where you have, think of it as a one-arm interventional study. You have one arm, in this case, that received the intervention, and now you have to go and look for a comparison or comparator that did not receive the intervention outside that environment. So it's a quasi-experiment. Quasi means kind of. It's kind of an experiment because you receive an intervention.
A pseudo experiment.
Exactly. But the other group did not receive an intervention outside the study. So you're going to compare, all right, these kids that received an intervention, how do they compare with the kids from the next community who did not receive an intervention, right? And so you might do a sample size selection and say, okay, we need 200 kids from this population, and we're going to select 200 kids from the next population, and we're going to measure, let's say, whatever the outcome is you're trying to measure, right? You're going to measure and compare between the 2 groups, and that will tell you whether the outcome was significant. Or if you had data on those children before they received the intervention, you can then compare before and after. And you can say, okay, wow, before the intervention, this was how they were. Now, this is how they were. So that allows you to make some kind of inference about the population. Then you're going to have a different study for mothers, lactating mothers. The same thing. You compare this group to another group that did not receive intervention. Or if you had data before, you compare before and after. Now, if you don't have all of that data, you can also still evaluate process indicators. Like the organization came and did some work. You can look at the records. You can look at, how many people did they treat? You can do a satisfaction survey of the mothers. Now, that is not telling you anything about effects of interventions, but at least it's still important because you can have a sense for how do the mothers feel. You can ask the mothers themselves, how do you, compared to 1 year ago, how do you feel now? And many things of that nature. Of course, with that kind of self-reported data, you will have a lot of biases, but it is better than nothing. So in case you don't have a comparator group, you can just survey those who received the intervention and say, on a scale of 1 to 10, how do you feel about the organization's interventions? How do you feel about your health compared to a year ago? how will you rate yourself now? You know, I feel better now, or I feel better 10 years ago, you know, 1 year ago, or things of that nature. So, you know, they say half bread is better than none. So if you don't have a comparator group and you don't have a time to design a complex study, you can just still do an evaluation survey of the people who received the intervention, and that will still give you some insights to make some statements. Does that
Thank
answer
you
your
very much, Prof. Thank you very much.
You're welcome.
Thank you, sir. Emmanuel, I think you are our last person for today. Emmanuel Andrew.
All right, Emmanuel has gone, so I can go to.
They are not here.
Thank you very much, Prof. I want to ask, you know, when you were explaining univariate analysis, you said that analysis will tell us what is the mean value of X. It's just focus on X. So I want to just ask, is it safe to also call that a kind of a descriptive statistics? More like, is it similar to the normal descriptive statistics that we have that will tell us the mean and all the rest?
Yeah, so yes, the answer is yes. And the answer is also that it is more complicated than that. So yes, every univariate analysis is a descriptive analysis, but descriptive analysis is not only limited to univariate analysis. You can also have bivariate analysis. You can also have multivariable analysis that are descriptive. For example, you can have an exploratory regression model that is just descriptive and nothing more than that. So the absence or presence of a particular analysis in of itself doesn't tell you about the design of a study. Because on the one hand, you will have issues of data analysis, which are quite different from issues of study design. The issues of design are, of course, are more important. They take bigger place in the grand scheme of things, because that's the design tells you everything about the study. The statistical analysis, well, not so much. But you can draw some inference from the analysis, but what we should really concern ourselves is what was the study design like. I hope that answers your question.
Hamidu, I believe this is an old hand, right? Okay. I think we are done, Prof. Thanks,
Okay.
everyone.
Awesome. I'm going to run away before somebody else raises their hand.
Thank you very much, sir.
All right. Thanks, everyone. Have a great weekend.
Thank you very much, Prof. Have
All
a
right,
great weekend, sir. Thank you.
Thank you. Yeah. All right. Bye.
Yeah.
Thank you, everyone.